Strawberry cake, brownies, and cheesecake are built with insane precision. You will see bright berry fillings folded into sponge, dense chocolate mix getting baked, and creamy cheese custard set smooth before the final wrap. Today, we follow every step on the line to reveal the machines and secret tricks that turn simple ingredients into the most delicious cakes that have ever crossed your mouth. The industrial strawberry layer cake manufacturing sequence begins at the bulk dry storage terminal. Large-scale suction blowers move sifted pastry flour into the primary weight hoppers. These hoppers utilize load cells to ensure a precision of within 100 grams. A secondary pneumatic line introduces powdered glucose into the flour stream. The glucose prevents the starch from retrograding during the freezing process. Sodium bicarbonate is injected at a ratio of 2 kilograms per metric ton of flour. This leavening agent reacts with acidic components to create the crumb structure. A Z horizontal ribbon blender rotates to achieve a 99% homogeneity rating. The hydration phase starts inside a twin-screw continuous mixing unit. Liquid whole eggs are metered into the chamber at a constant flow rate. These eggs are chilled to 5 degrees Celsius to prevent protein denaturation. A high-pressure pump injects vegetable oil through a series of micro nozzles. The oil coats the flour particles to inhibit excessive gluten development. Deionized water is added to reach a specific gravity of 1.05 for the batter. A jacketed cooling system keeps the mixing chamber at a steady 18 degrees Celsius. This temperature control is vital for the stability of the chemical leavening agents. The aeration stage uses a high shear rotostator head to incorporate nitrogen gas. Nitrogen provides a finer bubble structure than standard atmospheric air. The resulting batter density is measured by an inline densitometer. This device sends real-time feedback to the gas flow controller. A batter density of 0.45 grams per cubic centimeter is the target for this recipe. The batter travels through stainless steel piping to the manifold depositor. This manifold spans the width of a 1 meter wide steel conveyor belt. Individual piston pumps discharge 60 milliliters of batter into silicone-coated molds. The molds move into a direct gas-fired tunnel oven with 12 independent heat zones. Zone 1 operates at 140 degrees Celsius to facilitate initial lift. The belt speed is calibrated to ensure a 20-minute residence time. Moisture sensors at the midpoint monitor the humidity levels of the oven atmosphere. High humidity prevents the formation of a thick crust on the sponge surface. Zone 6 reaches a peak temperature of 190 degrees Celsius. This heat triggers the caramelization of surface sugars for color development. The final zones gradually reduce the temperature to set the internal cake matrix. Automatic vacuum depanners lift the baked sponges from the molds at the oven exit. The sponges are placed onto a modular plastic cooling belt. This belt travels through a HEPA-filtered cooling tunnel for 30 minutes. Ambient air is pulled through the sponges to remove internal heat. The core temperature must reach 22 degrees Celsius before the slicing phase. A battery of reciprocating serrated blades cuts the sponges into 3 equal layers. The blade height is adjusted by microservos based on laser thickness measurements. Each layer is diverted to a separate conveyor for specific ingredient application. The strawberry coulis production wing operates as a closed-loop thermal system. Frozen strawberry blocks are pulverized by a high-torque industrial crusher. The resulting slurry moves into a vacuum evaporator to concentrate the natural sugars. Evaporation occurs at 60 degrees Celsius to preserve the volatile flavor compounds. Liquid pectin is injected into the concentrate to establish a thermo-reversible gel. The pH is adjusted to 3.2 using a concentrated lemon juice buffer. This acidity is necessary for the pectin to form a stable molecular network. The coulis is then passed through a fine mesh filter to remove seeds. A plate heat exchanger cools the coulis to 8 degrees Celsius for immediate use. The first applicator station uses a waterfall distributor to coat the base layer. A weight check scale verifies that 40 grams of coulis are applied to each cake. The second sponge layer is placed on top by a high-speed vacuum pick-and-place unit. A second applicator deposits a layer of strawberry-infused cream over the middle sponge. This cream contains stabilized dairy fats and emulsified strawberry solids. The third sponge layer completes the vertical stack before the primary icing phase. The outer frosting is prepared in a pressurized aeration tank for maximum volume. Anhydrous milk fat is blended with sugar syrup and natural stabilizers. The mixture is whipped at 500 revolutions per minute under 3 bars of pressure. This process creates a stable foam with a shelf life of 12 days. The frosting is pumped to a dual-axis robotic icing station. The cake rotates on a pedestal while a side scraper applies the frosting. A top spreader levels the frosting to a thickness of 4 millimeters. Optical cameras inspect the coverage for any gaps or uneven patches. Decorative strawberry rosettes are formed by a multi-nozzle extrusion head. This head uses a star-shaped aperture to create the traditional fluted texture. The extrusion pressure is synchronized with the conveyor belt speed. A secondary station applies a fine mist of pectin glaze over the frosting. This glaze prevents the frosting from drying out during storage. Fresh strawberry quarters are placed into the rosettes by a vision-guided robotic arm. These strawberries are pre-treated with an ascorbic acid wash to prevent browning. A final dusting of pulverized dextrose is applied for visual contrast. The cakes enter a spiral blast freezer for rapid stabilization. Liquid carbon dioxide is sprayed into the chamber to reach minus 40 degrees Celsius. This rapid cooling creates small ice crystals to preserve the cake texture. The cakes spend 45 minutes inside the spiral freezer. An automated pusher arm moves the frozen cakes toward the packaging line. Cardboard flats are folded into boxes by a mechanical mandrel system. A plastic liner is inserted into each box to prevent moisture loss. The cakes are lowered into the boxes by a soft grip robotic hand. A metal detector scans every boxed cake for potential physical contaminants. This unit can detect ferrous particles as small as 0.5 millimeters. Any rejected boxes are diverted to a secondary inspection bin. A weight grader ensures the final product meets the 500-gram specification. The boxes are sealed with a tamper-evident adhesive strip. An inkjet coder prints the batch number and the production timestamp. The boxes are stacked into corrugated shipping cases by a robotic palletizer. These cases are then wrapped in polyethylene film for structural stability. The palletized goods are moved into the high bay cold storage warehouse. This facility uses an automated storage and retrieval system for inventory management. The temperature is maintained at minus 18 degrees Celsius with zero fluctuation. Loading docks are equipped with thermal seals to prevent heat ingress during shipping. Every delivery truck is monitored via GPS for real-time temperature tracking. This data is logged into the quality assurance database for compliance. The entire production line can output 800 cakes per hour. This efficiency is achieved through the total integration of mechanical and digital controls. The cleaning in place system cycles through the entire piping network every shift. Hot caustic solution removes fat deposits from the mixing and pumping units. A secondary acid wash neutralizes any mineral scale in the heating elements. The final rinse uses sterilized water to ensure a zero residue environment. All wastewater is treated in an on-site filtration plant before discharge. This plant recovers 90% of the water for non-food industrial use. The factory operates on a 24-hour cycle to maximize equipment utilization. This rigorous process ensures the consistency of the industrial strawberry layer cake. The air quality in the assembly room is monitored for microbial counts. Surface swabs are taken from the conveyor belts every 4 hours. These samples are incubated in the laboratory to check for yeast and mold. The flour silos are equipped with explosion venting panels for safety. Dust collection systems pull fine particles away from the mixing stations. The grease used in the mechanical bearings is food grade certified. All electrical panels are NEMA rated for protection against high pressure washdowns. The facility utilizes LED lighting to reduce heat generation in the cooling zones. The vegetable oil is stored in nitrogen blanketed tanks to prevent oxidation. These tanks are equipped with ultrasonic level sensors for inventory tracking. The sugar syrup is kept in heated vats to prevent crystallization. All raw ingredients are barcoded upon entry for full traceability. This allows the factory to track a single cake back to the specific wheat harvest. The conveyor motors utilize variable frequency drives for precise speed control. These drives reduce energy consumption during periods of lower production. The central control room monitors every motor and sensor in the building. The robotic arms are programmed using a proprietary motion control language. These programs allow for rapid changeovers between different cake sizes. The ultrasonic blades are sharpened using a specialized grinding unit every weekend. This maintenance ensures the cleanest possible cut for the sponge layers. The silicone molds are inspected for surface degradation after every 1,000 cycles. Worn molds are recycled to prevent any silicone migration into the batter. The packaging cardboard is sourced from sustainably managed forests. This commitment to materials ensures the long-term viability of the production model. The industrial fabrication of brownies begins with the high-volume intake of raw commodities. Bulk storage silos hold up to 50 tons of specialized pastry flour. This flour features a low protein content to ensure a tender crumb. Pneumatic transport lines move the flour into the primary sifting station. Vibratory screens remove any particles larger than 200 microns. Cocoa powder arrives in hermetically sealed containers to prevent moisture absorption. This cocoa is typically alkalized to reach a pH level of 7. The alkalization process darkens the powder and mellows the flavor profile. Automatic scales measure the cocoa with an accuracy of 10 grams. A separate line delivers granulated sucrose from a central hopper. The sugar is pulverized into a fine mesh to facilitate rapid melting. Liquid fats are stored in stainless steel vats with internal heating coils. These coils maintain the fat at a constant 45 degrees Celsius. This temperature prevents the lipid chains from crystallizing in the pipes. Refined soybean oil provides the necessary moisture for a fudgy texture. Some formulations utilize anhydrous milk fat for a richer mouthfeel. The primary mixing phase utilizes a high-torque industrial blender. The liquid fats enter the mixing chamber through pressurized nozzles. Cocoa powder is added next to create a thick chocolate paste. This stage is known as the wet rub in the baking industry. The friction from the blades raises the paste temperature slightly. Infrared sensors monitor this heat to prevent scorching of the cocoa. A secondary mixer prepares the hydration base for the batter. Liquid eggs are pumped from refrigerated tanks at 4 degrees Celsius. These eggs undergo inline pasteurization before they reach the blender. A plate heat exchanger flashes the eggs to 60 degrees Celsius. They are immediately cooled back to 10 degrees Celsius. This process eliminates pathogens without coagulating the egg proteins. Natural humectants, like vegetable glycerin, are added to the egg mix. Glycerin binds water molecules to the starch during the baking cycle. This chemical bond prevents the brownie from becoming stale. The dry ingredients meet the wet base in a continuous mixer. The flour is folded in by a twin-screw agitation system. This system prevents the overdevelopment of gluten in the wheat. Excessive gluten would make the brownie tough and bread-like. Salt is injected into the stream at a precise 0.2% ratio. It acts as a flavor enhancer for the chocolate components. A small amount of sodium bicarbonate provides a chemical lift. This leavening agent reacts with the acidic cocoa particles. The batter moves through a series of refining rollers. These rollers reduce the particle size of the sugar and cocoa. A final particle size of 30 microns ensures a smooth mouthfeel. The refined batter is pumped into a vacuum de-aeration tank. This tank removes any trapped air bubbles from the mixing stage. Removing air increases the density of the final brownie slab. A dense structure is required for the fudge classification of the product. The batter reaches a final viscosity of 15,000 centipoise. Industrial brownies often feature inclusions like semi-sweet chocolate chips. These chips are stored in a climate-controlled room at 18 degrees Celsius. This prevents the chips from blooming or sticking together. A vibratory feeder dispenses the chips into the moving batter line. A static mixer folds the inclusions in without shearing them. The ratio of inclusions is usually 10% of total weight. The batter is now ready for the depositing stage. A high-speed manifold spans the width of the production conveyor. This manifold contains 24 individual piston-driven nozzles. The nozzles deposit the batter into large steel baking trays. These trays are coated with a permanent Teflon layer. An automated sprayer applies a secondary film of vegetable oil. The oil ensures a clean release after the cooling phase. Each tray receives exactly 12 kilograms of brownie batter. Optical sensors verify the weight and level of every tray. A mechanical oscillating plate spreads the batter to the corners. This ensures the brownie slab has a uniform thickness of 30 millimeters. The trays enter a multi-zone convection tunnel oven. The oven is 60 meters long to accommodate high-speed production. It is heated by a series of natural gas burners. The first zone is set to 150 degrees Celsius. This initial heat initiates the melting of the sugars. The second zone increases the temperature to 170 degrees Celsius. This is the primary, baking phase where the structure sets. Convection fans circulate the air at 5 meters per second. This constant airflow ensures the edges do not burn before the center. Steam injection ports maintain a 40% humidity level. The humidity prevents the top surface from cracking or crusting. The final oven zone facilitates the Maillard reaction. This chemical reaction occurs between the sugars and amino acids. It creates the complex flavor profile associated with baked chocolate. The total residence time in the oven is 28 minutes. An automated arm extracts the hot trays at the oven exit. The trays move onto a modular plastic cooling belt. This belt travels through a spiral cooling tower. Filtered air at 15 degrees Celsius blows across the trays. The cooling process must be gradual to prevent the slab from shrinking. The internal temperature must drop to 25 degrees Celsius. This cooling phase typically lasts for 45 minutes. A vacuum depanner lifts the entire brownie slab from the tray. The slab is placed onto a high-density polyethylene cutting board. This board moves toward the ultrasonic slicing station. Ultrasonic blades vibrate at 20,000 Hz per second. This vibration prevents the dense brownie from sticking to the knife. The blades make vertical and horizontal cuts simultaneously. This creates perfectly square units with sharp edges. The standard size is 5 centimeters by 5 centimeters. Any trim from the edges is diverted to a rework bin. This trim is ground up for use in other chocolate products. The individual brownie units are separated by a divergent conveyor. This conveyor increases the space between the brownies for packaging. Some brownies pass through an enrobing station for a chocolate coating. The enrober pours a curtain of tempered chocolate over the units. A blower clears the excess chocolate to maintain a thin layer. The coated brownies enter a secondary cooling tunnel. This tunnel sets the chocolate coating to a high gloss finish. The brownies move into the primary packaging zone. A robotic arm picks up 4 brownies at a time. It places them into a pre-formed plastic blister tray. The tray provides structural support during shipping and handling. A flow wrap machine encapsulates the tray in a polymer film. This film is treated with a nitrogen flush. Nitrogen replaces the oxygen to prevent the oxidation of fats. This gas flushing technique doubles the product's shelf life. The film is heat sealed at both ends by a rotating jaw. A laser printer applies the lot number and expiration date. The individual packs move toward the secondary packaging station. A case packer assembles 24 packs into a corrugated box. This box is sealed with a pressure-sensitive adhesive tape. A check weigher verifies that the case meets the target weight. Any underweight cases are automatically pushed off the line. A palletizing robot stacks the cases onto a wooden pallet. The robot follows a specific pattern to ensure stack stability. A stretch wrap machine secures the load with several layers of plastic. The pallet is tagged with a radio frequency identification label. This label contains the entire production history of that batch. The pallets are moved to a temperature-controlled warehouse. This warehouse is kept at 18 degrees Celsius. Quality control technicians perform a moisture analysis on every batch. They use a halogen moisture analyzer to check for consistency. The target moisture content for a fudge brownie is 12%. A texture analyzer measures the force required to compress the brownie. This ensures the chewiness meets the brand specifications. The cocoa solids are verified using a spectrophotometer. This device measures the light absorbance of the chocolate. The production line operates on a 24-hour schedule. A clean-in-place system sanitizes the mixes between batches. This system uses hot water and biodegradable and detergents. All water used in the plant undergoes reverse osmosis filtration. The factory utilizes a closed-loop energy recovery system. Heat from the ovens is captured to preheat the incoming air. This reduces the carbon footprint of the manufacturing facility. The flour silos are equipped with explosion suppression systems. Fine flour dust can be highly combustible in large volumes. Spark detectors monitor the pneumatic lines for any heat buildup. The packaging room is kept at a positive air pressure. This prevents any dust or insects from entering the clean zone. Workers wear specialized lint-free suits and head coverings. All tools are made from detectable stainless steel. The vegetable oil tanks are nitrogen blanketed to prevent rancidity. Oxygen is the primary enemy of long-term fat stability. The supply chain is tracked using a digital ledger system. Every ingredient can be traced back to its original farm. This level of transparency is standard for industrial food. Production. The brownie recipe is stored in a secure digital vault. The central computer controls every motor and valve in the plant. The automated manufacturing of cheesecake begins with the large-scale processing of the base crust material. Bulk quantities of graham flour and wheat flour are combined in a high-speed industrial shredder. This unit pulverizes the baked biscuits into a uniform crumb with a diameter of 2 millimeters. The crumbs are moved via a vibratory conveyor to a horizontal blending drum. Molten butter is injected into the drum through a series of atomizing nozzles. The butter acts as a binding agent to ensure the crust remains structurally sound. Granulated sugar is added to the mixture to facilitate caramelization during the baking stage. The crust mixture is transferred to the primary molding line by a vacuum lift system. Circular spring-form pans move along a specialized belt at a rate of 40 units per minute. A volumetric depositor drops exactly 1 100 grams of the crumb mixture into each pan. A pneumatic tamping head descends to compress the crumbs with 50 pounds of pressure. This compression creates a dense and level foundation for the cheese filling. The sides of the pans are simultaneously brushed with a light film of release agent. This prevents the cake from adhering to the metal during the cooling phase. The preparation of the cheese filling occurs in a separate, climate-controlled mixing terminal. Industrial-sized blocks of cream cheese are loaded into a vertical, high-shear mixer. These blocks are tempered to exactly 20 degrees Celsius to ensure maximum pliability. A heavy-duty agitation arm breaks the cheese down into a smooth and aerated paste. Liquid sour cream is introduced through a flow-controlled piping network. The sour cream provides the necessary acidity to balance the richness of the fats. Large quantities of liquid whole eggs are then metered into the mixing chamber. These eggs act as the primary emulsifier and structural setting agent for the batter. Pure vanilla extract is injected into the stream via a micro-dosing pump. The mixing speed is reduced to avoid the over-incorporation of atmospheric air. Excess air in the batter causes the cheesecake to crack during the thermal expansion phase. The batter is monitored by an inline viscometer to ensure it reaches 4,000 centipoise. A final stage of the mixing process involves the addition of cornstarch. The starch binds to the free moisture to prevent the occurrence of syneresis. The finished batter is pumped through insulated stainless steel lines to the depositing station. A multi-piston manifold accurately dispenses the batter over the prepared crust. Each pan is filled to 90% of its total volume to allow for expansion. The pans are then transferred into a continuous water bath tunnel oven. This oven utilizes a shallow pool of circulating water to regulate the heat transfer. The water bath ensures the temperature never exceeds 100 degrees Celsius at the base. This thermal regulation prevents the edges of the cake from cooking faster than the center. The oven is divided into 4 distinct thermal zones for precise moisture control. Zone 1 maintains a high humidity level of 80% to prevent surface drying. The temperature in this initial stage is set to 120 degrees Celsius. Zone 2 increases the heat to 140 degrees Celsius to set the egg proteins. The moisture levels are gradually reduced in Zone 3 to facilitate color development. A light golden hue is achieved on the surface through controlled convection airflows. The final zone utilizes a cooling gradient to stabilize the cake before it exits the oven. The total residence time within the tunnel oven is approximately 90 minutes. An automated arm removes the pans from the water bath at the end of the line. The cakes enter a primary cooling chamber to reduce the internal temperature to 40 degrees Celsius. This slow cooling prevents the cheesecake from pulling away from the sides of the pan too quickly. The pans move into a blast chiller where the temperature is dropped to 4 degrees Celsius. This rapid cooling stage is essential for the final set of the dairy fats. The cheesecake must reach a firm consistency before the depanning process begins. A mechanical depanner uses a series of gentle suction cups to lift the cake from the mold. The springform rings are automatically expanded and retracted for sterilization. The cakes are placed onto a sanitized plastic transport disc for the finishing stage. Many industrial cheesecakes receive a fruit-based topping at this point in the sequence. A secondary manifold applies a layer of fruit puree or glaze to the top surface. The glaze is heated to 60 degrees Celsius to ensure a smooth and glass-like finish. It is immediately cooled by a localized cold air jet to lock the topping in place. If the recipe requires a swirl pattern, a robotic needle system is utilized. The needles inject colored fruit syrups into the wet batter before the baking stage. The robotic arm follows a pre-programmed geometric path to ensure visual consistency. For decorative borders, a multi-nozzle whipping station applies cream cheese frosting. The frosting is extruded through fluted tips to create a traditional rosette pattern. The cakes then move to the high-frequency ultrasonic slicing station. The ultrasonic blades vibrate at 30,000 Hz to prevent the cheese from sticking. This technology allows for perfectly clean cuts through the dense and sticky filling. The machine can slice the cheesecake into 12 or 16 equal wedges. Each wedge is separated by a thin piece of parchment paper to prevent re-adhesion. The parchment paper is fed from a continuous roll and cut by the same blade. The sliced cakes are moved to the primary packaging terminal by a synchronized conveyor. The packaging process involves placing the cake into a rigid plastic dome. This dome protects the decorative frosting and the delicate top glaze. A cardboard base provides structural support and contains the product information. The packages are moved into a vacuum sealing machine to remove excess oxygen. An inert gas flush is sometimes used to maintain the freshness of the dairy components. The sealed units are then placed into individual retail boxes by a pick-and-place robot. These boxes are constructed from high-grade recycled paperboard with a moisture barrier. A laser printer applies the batch code and the specific expiration date to each box. The boxes are grouped into master cases for bulk distribution to wholesalers. Each master case is tracked by a unique radio frequency identification tag. The cases are stacked on pallets by a heavy-duty robotic palletizing arm. The pallets are wrapped in multiple layers of clear stretch film for stability. The finished product is stored in a deep freeze warehouse at -20 degrees Celsius. This freezing stage allows for long-distance transport without compromising the texture. The quality control department monitors the fat content of every batch using a centrifuge. The moisture to solids ratio is checked using a rapid thermal analyzer. Any batch that falls outside of the 5% variance range is rejected. The pH level of the batter is measured to ensure the sour cream has reacted correctly. A texture analyzer probes the center of a sample cake to measure the resistance. This ensures the mouthfeel is consistent across every single production run. The color of the top glaze is verified using a digital spectrophotometer. The industrial facility uses a centralized control system to manage the ingredient flow. Silos are equipped with ultrasonic level sensors to trigger automatic reordering. The water used in the process undergoes a 3-stage purification sequence. This includes carbon filtration and ultraviolet sterilization to ensure purity. The air in the assembly room is filtered through a series of HEPA units. These filters remove nearly all airborne contaminants from the production environment. The floors are sloped to integrated drainage systems for easy cleaning. Every 4 hours, the entire line undergoes a localized sanitation cycle. High-pressure steam is used to clean the depositor nozzles and mixing blades. The conveyor belts are constructed from antimicrobial blue polyurethane material. This material resists the growth of bacteria and is easy to inspect visually. The factory operates on a 24-hour schedule with 3 shifts of workers. The output can reach several thousand units per hour depending on the cake size. This massive scale is necessary to meet the global demand for frozen desserts. The supply of cream cheese is delivered via refrigerated tanker trucks. These tankers are emptied into the holding vats using a pressurized air system. The butter is stored in a separate heated room to maintain a liquid state. All dry ingredients are passed through a metal detector before entering the mixer. This ensures that no foreign objects from the harvesting process remain in the flour. The packaging materials are stored in a dry zone to prevent mold growth. The logistics team coordinates the departure of refrigerated trucks every 6 hours. The industrial process of bread production begins not with baking, but with an orchestrated balance of mechanics and chemistry where every gram of input is measured every rotation of a blade is timed, and every degree of heat is calculated long before the first loaf begins to take shape. The cycle starts in the mixing room, where automated ingredient handling systems transport vast quantities of flour through pneumatic conveyors, drawing it from silos positioned outside the facility and funneling it in clouds of fine white powder into stainless steel batch hoppers that feed into the primary dough mixers. These mixers, towering and gear-driven, don't simply stir. They press, fold, and stretch the mixture with rotating arms that mimic the pressure and pull of hands, but at a scale and speed no human could replicate. At the moment liquid meets dry, the system kicks into life, and the rhythm of kneading begins. Inside the mixing chamber, every second counts. The speed starts slow to allow hydration, gradually increasing as gluten strands form and interlace, building the elastic structure that will define the shape, rise, and texture of the finished bread. Temperature sensors within the dough track the frictional heat produced during mixing, while torque sensors monitor resistance to ensure the dough reaches a consistent development profile. Cooling jackets around the mixer basin activate if necessary, keeping the dough within its ideal thermal range to avoid overproofing later in the process. Once the target consistency and elasticity are reached, soft, slightly tacky, extensible, but resilient, the dough exits the mixer through a bottom hatch, sliding as one heavy, cohesive mass into the next stage. A sheeter receives the dough next. Twin rollers compress it into a continuous slab, which then moves through a series of gauges to ensure thickness and density remain exact. This is not a shaping step, it's preparation. The flattened dough is directed into a high-capacity divider where a series of volumetric pistons cut the slab into uniform portions. These pistons measure by volume rather than weight, ensuring that even as humidity or temperature fluctuates slightly, each piece contains the exact same mass of air and dough combined. Once divided, the pieces are dropped into intermediate proofers, tall, climate-controlled chambers where the dough rests in a carefully maintained environment of warmth and humidity. It's here that the dough begins to ferment actively for the first time. The yeast, having been activated during mixing, releases carbon dioxide, expanding the structure from within. But this step isn't about final rise. It's about conditioning the dough, allowing it to relax after the physical stress of division so it can be molded without tearing. After a set number of minutes, each portion travels via conveyor to the molder. A set of guide rollers gently flattens the dough again. Then curling belts begin to shape it, rolling the mass inward to form a tight spiral that will become the loaf's interior structure. Pressure plates calibrate tension precisely, ensuring the outer skin of the dough wraps around the inner layers tightly enough to support rise, but not so tight that the loaf bursts during baking. Once molded, the loaves drop gently into metal baking pans, moving along a wide belt. Each pan is pre-lubricated with a fine mist of oil dispensed by a jet spray system to ensure clean release after baking. At this point, the pans pass through the final proofer, a long, enclosed tunnel where heat and humidity are kept within strict boundaries. Here, the loaves experience their final rise, swelling as fermentation accelerates. The gases trapped in the dough expand, the gluten matrix stretches to accommodate the volume, and the surface tension pulls tight, smoothing the top into a rounded dome. Sensors along the proofer track height, spacing, and proofing time. Any variation is logged, and the system will adjust conveyor speed or proofer climate to compensate. If the dough rises too quickly, the texture becomes irregular. Too slowly, and the crust may blister or fail to color evenly. Timing here is crucial. Baking must happen at the peak of fermentation activity to lock in that volume. Once the proofing cycle finishes, the pans emerge from the chamber and feed directly into the oven. The industrial oven is a continuous tunnel design, divided into multiple thermal zones with independent top and bottom heat controls. As the pans enter, steam injectors release a high-pressure burst across the loaf tops. This initial moisture keeps the crust soft in the early minutes, allowing for maximum oven spring as the bread expands rapidly under intense heat. The steam also sets the crust structure and eventually contributes to its color and gloss. The baking process unfolds in stages. First comes expansion, where gases expand, alcohols evaporate, and enzymes break down residual sugars. Then comes gelatinization, as starches swell and set. Finally, Maillard reactions begin on the surface, turning the pale, supple dough into a rich, caramel-toned crust. The belt moves at a steady pace, calibrated so that by the time each loaf exits the last zone, it has reached the exact internal temperature required for complete bake, usually just over 96 degrees at the core. Exiting the oven, the loaves are hot and fragrant, but far too fragile for packaging. They roll forward on the conveyor and enter a spiral cooling system, a towering structure of coiled belts that winds upward, allowing the loaves to circulate through cooler air over the course of 30 to 40 minutes. Fans direct airflow from multiple angles, and vents above the line extract excess humidity to avoid condensation forming on the crust. As the temperature gradually drops, the crumb sets fully and moisture redistributes inside the loaf, ensuring softness remains throughout shelf life. Once cooled, the pans reach the depanning machine. A rotating arm, fitted with suction cups, lifts each loaf upward with precision timing, placing it onto a transfer belt while the empty pan continues onto a cleaning line. The pans are scrubbed with mechanical brushes, sprayed with sanitizer, and then dried by air knives before being stacked or returned to the molder for the next round. Meanwhile, the bare loaves now advance towards slicing and packaging. If the bread is destined for sale as whole loaves, it bypasses this stage, but most continue on to the slicer. This machine is built for speed. Multiple blades, mounted vertically in a row, oscillate at high speed as each loaf is pushed through by a belt-driven ram. The slices fall into alignment instantly, held together by guide rails as they move forward still in loaf shape. The next step is bagging. A plastic bag is blown open by a quick burst of air and guided into place by forming horns. The sliced loaf drops in, and a closing device, either a twist tie, tamper band, or plastic clip, seals the bag in one motion. An inline printer stamps each bag with a code indicating date, time, production line, and batch number. The sealed loaf is then guided onto a secondary conveyor for inspection. Cameras and weight sensors scan every packaged loaf. Any irregularities in size, shape, color, bag print, or closure are instantly flagged. Rejected loaves are diverted automatically, while the accepted product continues forward to be grouped for carton packing. Robotic arms pick up loaves in sets and stack them into shipping boxes, which are then sealed, labeled, and passed to the palletizer. The palletizing system uses multi-axis robotic arms to stack cartons onto wooden pallets in precise formations designed to prevent shifting or damage in transport. Slip sheets are placed between layers for stability. Once full, the pallet enters a stretch wrapper, where plastic film binds the load tight from base to top. A printed label is applied to the outer edge of the film, detailing product information, origin, destination, and tracking codes. Every action in this process is overseen by a centralized control network that connects mixers, dividers, molders, ovens, coolers, and packers into one coordinated line. Data flows constantly between stations. If the divider senses a shift in dough density, the molder adjusts tension. If the oven reports inconsistent browning, the slicer slows slightly to sync packaging output. Everything is in motion, yet everything is balanced. In a large-scale factory dedicated to the continuous assembly of sandwiches, every stage is a precisely engineered operation where timing, alignment, and consistency converge across hundreds of feet of synchronized machinery. And the process begins long before the first sandwich reaches the wrapper. It starts with bread loaves, already baked, cooled, and brought into the slicing system in racks, where they are automatically depanned, aligned, and fed into high-speed slicers fitted with ultra-sharp, serrated, or ultrasonic blades that oscillate thousands of times per second to deliver uniform, clean-edge slices without compressing the soft interior crumb or fracturing the crust. Once sliced, the bread slices travel by conveyor to a pre-alignment station, where camera-guided sensors and rotating guide arms ensure every slice is positioned in the exact orientation required for the next phase, which is the laying down of the base slices. These are distributed in pairs or rows, depending on whether the line is configured for single or multiple sandwich formats, and set evenly onto the moving belt with equal spacing between each set. The flow is constant, with no interruption between batches, and any variation in slice thickness or alignment is corrected in real time by pneumatic actuators and servo-driven guides that subtly adjust position and speed without halting the line. As the bottom slices approach the filling zones, the first application arrives in the form of spread, be it mayonnaise, mustard, aioli, butter, or any other emulsified or creamy base. A series of nozzles or roller spreaders applies a controlled layer, often using pulse pressure, to shoot a fan of spread across the surface, which is then evened out by a soft-tipped roller or oscillating blade to ensure consistent coverage all the way to the edges of the bread. Sensors mounted above each lane scan the surface to confirm the presence, distribution, and thickness of the spread. And if coverage falls below specification, a feedback loop either reapplies the layer or removes the sandwich from the line. After the base layer is applied, the sandwich moves into the protein zone. Here, pre-sliced meats such as turkey, ham, beef, chicken, or plant-based alternatives arrive from upstream feed systems, where they have been portioned, weighed, and fanned into stacks by centrifugal feeders or vibratory shakers. These stacks are lifted by robotic pick-and-place arms equipped with vacuum suction or gripper fingers, depending on the product's texture, and laid gently onto each bread base with alignment controlled by high-speed imaging systems that adjust position in real time to match the orientation of the incoming slice. Every portion is weighed by inline check weighers before being applied, ensuring that each sandwich receives a uniform protein layer, with rejections happening instantly and automatically if tolerances are exceeded. Next comes the cheese layer, which moves from chilled stacks through a peeling and singulation system that separates individual slices, removes any protective film, and transfers them to a placement module. The cheese is picked and placed onto the meat with exact positioning, sometimes staggered depending on the sandwich style, and lightly pressed to ensure it conforms to the underlying surface without folding or hanging over the edge. The equipment adjusts for slice fragility using low-pressure vacuum heads and static control to prevent light cheeses from sticking to conveyors or deforming during placement. Vegetables come next, and this stage is often the most complex due to the variability in size, moisture, and fragility of the ingredients. Lettuce is dispensed from overhead hoppers with calibrated vibratory trays that gently shake shredded or leaf lettuce onto the sandwiches in measured volume, distributed evenly by spinning diffusers that sweep across the width of the belt. Tomatoes, cucumbers, and other sliced produce are fed from rotary magazines that release single slices in sequence, timed to the belt's movement, so each tomato lands directly at the center of the sandwich, guided by small airflow puffs or mechanical nudges if needed. Onion rings and other light layers are dispensed from spiral feeders or drop chutes, often with the assistance of static eliminators and light misting systems that prevent separation or clumping as the vegetables fall into place. If the top slice requires its own spread or condiment layer, a mirrored version of the first spreading station appears here, applying the layer just moments before the slice is joined to the assembled base. The top slice is picked by robotic arms from a secondary line of aligned bread slices, flipped if necessary depending on crust orientation, and gently pressed onto the assembled sandwich with just enough force to compress the stack into a unified structure without squeezing out fillings or deforming the shape. At this stage, the sandwich enters the compression and forming section. A series of soft rollers or belt presses applies uniform downward pressure to stabilize the build, enhance bite adhesion, and ensure the sandwich holds together through slicing, wrapping, and handling. The compression rollers are timed precisely to match belt speed, and the pressure profile is tuned to the product type, with more delicate sandwiches receiving lighter contact and denser builds compressed more firmly to lock the layers in place. Now fully assembled, the sandwich proceeds to the slicing station, where high-speed rotary or ultrasonic blades divide the product into the desired shape, typically halves or triangles. The slicing system is mounted on actuators that follow the motion of the sandwich as it moves along the belt, ensuring the blade enters and exits the loaf cleanly without tearing or pulling. Blade tension, sharpness, and angle are maintained through automated diagnostics, and the entire slicing module is flushed and sanitized between shifts to prevent cross-contamination. Cut sandwiches are now directed into the inspection lane, where overhead cameras and weight sensors verify slice alignment, edge definition, symmetry, and overall appearance. If a sandwich is misaligned, overfilled, underweight, or damaged during slicing, it is ejected by air blast or mechanical diverter before it reaches the wrapping system. The accepted sandwiches pass into the packaging zone, where the method of wrapping depends on the product's end use. For flow-wrapped sandwiches, the product enters a film feed tunnel where printed plastic film is drawn over and around the sandwich by guide belts, sealed along the back and ends by heated jaws that press and crimp the film closed in less than a second. A date coder prints production information onto the film surface just before the end seal. For chilled sandwiches sold in wedges or clamshells, the product is inserted by pick-and-place units into pre-formed rigid plastic containers. The lid is pressed or snapped into place and sealed with adhesive label strips or heat-sealed foil, depending on product design. Transparent sections are aligned with the sandwich face to ensure maximum visibility on shelf. Once wrapped, the sandwiches are grouped for boxing. A case packer counts the products and loads them into corrugated cartons, aligning each stack for minimal movement during shipping. Cartons are formed automatically from flat blanks fed into a forming station, sealed with hot melt glue or folded tabs, and labeled on the fly with barcodes, lot numbers, and shipping data. Each carton is scanned and weighed, and any deviation is flagged for inspection. The approved boxes move to the palletizing cell, where robotic arms stack them onto wooden or plastic pallets with layer patterns designed to balance weight and prevent shifting. The pallets are then rotated through a stretch wrapping station where film is applied under tension from bottom to top, stabilizing the entire load for transport. A final label is printed and applied to the side of the pallet with a scanner-readable code containing the production batch, shift, line number, and timestamp. Bagel production at factory scale is a continuous ballet of movement and transformation, where the dense, chewy character of each finished product is the result of precisely sequenced operations carried out by synchronized machines, each tuned to interact with dough in a way that preserves its integrity, develops its structure, and creates the exact conditions required for that unmistakable crust and crumb. It all begins in the dough room, where flour moves from towering silos into enclosed conveyor tubes, descending by weight into a batcher that draws measured volumes of water, salt solution, yeast suspension, and additional agents through chilled, jacketed feed lines that maintain temperature consistency from the first pump to the final discharge into the mixer. As the ingredients come together in a high-capacity spiral mixer, the arms begin turning slowly, cutting through the thickening mass with powerful, spiraling force, pulling the flour into the water and folding the developing dough inward from all angles. Unlike lighter breads, bagel dough requires far more resistance and strength, so the machines are set to operate under heavier torque, and the texture is intentionally firmer from the start. Temperature probes track internal friction heat. If the dough rises beyond the target, a cooling system kicks in, circulating chilled water through the ball's outer jacket, allowing the dough to strengthen and ferment without overheating. The mixing continues until the dough becomes tight, elastic, and resilient to touch, ready not for shaping, but for division. At this point, the dense dough is released through a bottom hatch and fed directly into a portioning unit that slices it into thick, consistent strips, each one calibrated for weight and volume by servo-guided sensors that track the length, width, and compression of the dough strand as it moves forward on the belt. These portions are then carried forward to the bagel former, a specialized system unique to this category of baked goods. Here, each dough piece is rolled into a rope between two textured conveyor belts, gradually tapering the ends for seamless closure. The ropes are then transferred to the forming drum, a rotating cylinder fitted with a center plunger and an outer ring guide that picks up the rope, curls it into a circle, and presses the ends together into a seamless loop without pinching, tearing, or folding. Formed bagels are deposited onto a wide, dusted conveyor belt, each one spaced perfectly from the next by indexing arms that keep rows uniform as they head toward the proofing section. At this stage, the dough is still dense and compact and needs controlled time to relax and ferment before any further processing. The trays of raw bagels enter an enclosed, temperature and humidity regulated proofer where warm, moist air surrounds the dough, gently encouraging expansion without aggressive rise. Over the next 15 to 20 minutes, the yeast becomes active, releasing carbon dioxide and creating a subtle softness beneath the taut exterior. Proofing times are controlled to the minute, with sensors tracking volume gain and relative humidity in every lane of the chamber, so that every bagel arrives at the next step with the same bounce, shape, and tension. What follows is the defining characteristic of bagel production: boiling, or more accurately, a high-temperature water bath that sets the outer crust before baking begins. As the proofed bagels exit the chamber, they move onto a boiling belt that carries them through a long stainless steel trough filled with circulating water, often mixed with barley malt or a similar solution to enhance browning later in the oven. The bagels float as they enter, and a set of rotating paddles gently submerge each one to ensure even exposure. They spend only seconds in this bath, but it's enough to gelatinize the starches on the surface, locking in shape and creating the foundation for that dense, glossy crust. Once boiled, the bagels are lifted from the water by an upward sloping mesh belt and allowed to drain momentarily before entering the topping section, where optional finishes, sesame, poppy, onion, salt, are applied. This happens through a combination of timing, moisture, and gravity. The wet surface of each bagel acts as a natural adhesive, so as they pass under overhead hoppers or through rotary topping applicators, the seeds or seasonings fall onto the dough and stick cleanly to the surface. Excess toppings are collected by a vibrating reclaim system beneath the belt, filtered and returned to the hopper for reuse, ensuring nothing is wasted and every bagel receives an even coating. The topping section leads directly into the oven, a massive tunnel-style system divided into multiple thermal zones that gradually bring the bagels from boiled to baked over the course of 10 to 12 minutes. The first zone introduces radiant heat to activate oven spring, but because the crust is already partially set, expansion is modest, and the shape remains tight and uniform. In the middle zone, the crust begins to brown, driven by Maillard reactions that create the deep caramel tones and toasty aroma typical of well-baked bagels. The final zone balances color and internal moisture, holding a slightly lower heat to allow the core temperature to rise without burning the toppings. Throughout the bake, airflow is precisely directed, and humidity is adjusted by steam injection valves to control crust thickness and finish. As they exit the oven, the bagels are fully formed, firm to the touch, richly colored, with a light sheen from the boiling stage and a tightly structured crumb inside. But at this point, they're still over 90 degrees Celsius internally and too hot for packaging, so the belt carries them into a spiral, cooling tower, a towering column of coiled belt that winds upward, allowing each bagel to travel along a rising path while being cooled by ambient air and filtered ventilation. Over the next 20 to 30 minutes, the internal temperature drops steadily and the crust stabilizes, preventing condensation and preserving the chewy exterior texture. From the base of the spiral, bagels are sorted by product type: plain, topped, seeded, and diverted into corresponding packaging lanes. If they are to be sold whole, they continue uncut, passing through alignment rails and into flow wrapping tunnels, where printed film encloses them in a tight, sealed wrap that's closed by heat-sealed seams on the underside. For multi-packs, bagels are counted and stacked automatically, transferred into trays or bags using pneumatic plungers or robotic suction heads, and sealed with clips, twist ties, or tamper-proof labels. Batch codes, production times, and expiration dates are printed by inline thermal inkjet systems on the package surface. If the bagels are destined for pre-sliced use, they proceed to the slicing unit, where a high-speed circular blade, often with ultrasonic vibration, cuts horizontally through each bagel's midpoint, while the product is held firmly in a compression cradle that prevents movement or tear out. The two halves remain paired and are then rewrapped as a sliced unit, ready for sandwich use or toasting. The sliced bagels are also inspected by weight, diameter, and color, with overhead cameras tracking any deviation in cut depth or alignment and removing out-of-spec product instantly from the conveyor. From there, the finished and packaged bagels are transferred into carton loading stations. A mechanical arm stacks them into pre-formed boxes, which are then sealed, labeled, and conveyed to the palletizing zone. Here, a robotic palletizer organizes the cartons in tight formations, applying slip sheets between layers and wrapping each pallet in film to protect it during transport. Each pallet is labeled with a scannable tracking code that contains all relevant production data: time, line, operator, batch, and destination. Throughout this entire process, every machine, every transfer, and every transformation is governed by a central control system that monitors line speed, batch integrity, ingredient flow, humidity, oven temperature, belt timing, and packaging rates. Adjustments happen automatically. If the boiling water cools by 2 degrees, the belt speed slows. If the oven heat drifts too high in zone 3, airflow is redirected. If the topping adhesion falls below threshold, an alert is triggered, and the hopper motor pulses slightly to shake more seed onto the line. Nothing here is guesswork. Everything is calculated. Bagels don't just bake. They're shaped, built, boiled, and finished by systems that never stop watching, adjusting, and maintaining perfect rhythm. The machines don't work alone, but in coordinated layers, each one tuned to preserve the dense structure, glossy crust, and unmistakable bite that defines a factory-made bagel. In just over an hour, a lump of flour and water is transformed into something firm, chewy, finished, and sealed, ready to ship, ready to slice, ready to toast, and repeated thousands of times per hour without pause. Molten butter streams across a sheet of dough, the first movement in the making of a croissant. Inside a modern factory, The air smells like yeast and warm flour, rich and comforting. But the scene is less like a bakery and more like an engineering lab. Stainless steel rollers, climate-controlled rooms, sensors, and conveyors stretching as far as the eye can see. Each golden, flaky croissant begins here in a choreography of temperature, timing, and touch, designed to turn flour, water, butter, sugar, and yeast into hundreds of delicate layers that rise and shatter with every bite. It starts with the dough. In an enormous spiral mixer, hundreds of kilograms of flour pour in from overhead silos, joined by measured streams of water, milk, sugar, salt, and blocks of softened yeast. The machine hums steadily, kneading the mixture into a smooth, elastic mass. The balance here is precise. Too little water, and the dough tears during rolling. Too much, and it turns sticky and uncontrollable. Sensors inside the mixer measure torque and resistance, automatically adjusting speed until the dough reaches exactly the right consistency. Stretchy, but not tough. As the mixer spins, the smell of fermentation begins to bloom. Sweet, faintly alcoholic, and alive. After about 10 minutes, the dough is released into a trough and left to rest. This resting stage, called bulk fermentation, allows the gluten to relax and the yeast to awaken. The dough rises slowly, filling the air with carbon dioxide bubbles that will help form the delicate crumb later. While at rest, butter is prepared. Croissant butter isn't just any butter. It's high in fat, low in moisture, and chilled to an exact temperature, usually between 12 and 16 degrees Celsius. At this stage, butter behaves more like clay than fat. It bends, doesn't crack, and can be shaped into perfect sheets. In the factory, large blocks are pressed through rollers until they form thin slabs as wide as the dough itself. Workers refer to this step as tempering the butter, but in truth, it's all about physics. The butter must be soft enough to fold, but firm enough not to melt when it meets the dough. The next step is lamination, the art that defines croissants. On the laminator, a massive conveyor stretches out like a runway, often over 15 meters long. The dough, now rested and pliable, rolls out into a wide rectangle several centimeters thick. A mechanized arm lays the butter sheet directly on top, perfectly centered, then folds the dough over it like an envelope. Hydraulic rollers compress the layers together gently, sealing the butter inside. This laminated block now begins its transformation into hundreds of layers. It passes through rolling machines that lengthen and flatten it, then folding stations that double or triple it repeatedly. Each fold multiplies the number of layers exponentially, from 2 to 4, 4 to 8, 8 to 16, until the dough contains up to 81 wafer-thin strata of butter and dough. Between each pass, the sheet travels through a cooling tunnel, chilled to just above freezing. This keeps the butter firm, preventing it from blending with the dough. Without that temperature control, the butter would melt and leak out, destroying the structure before baking. The sound of the lamination room is constant. Rollers whirring, compressors humming, dough sheets flapping lightly against steel. The air smells faintly of butter and flour, and everything glistens under the bright lights. Workers monitor thickness gauges and adjust tension controls, ensuring every sheet remains perfectly even across its width. A difference of half a millimeter could alter the final texture dramatically. Once laminated, the dough rests again to relax the gluten, then it's time for shaping. Massive guillotine cutters slice the sheets into long triangles, each destined to become one croissant. The triangles travel on conveyors toward an automated rolling machine. There, a soft brush flicks off excess flour, and mechanical fingers gently grip each triangle's base. The belt moves forward, and the dough rolls onto itself 3 times, tucking the tip under neatly. In a blur of motion, hundreds of croissants take shape every minute, each one coiled with perfect precision. If the croissant line includes filled varieties like chocolate or almond, the process adjusts. Before rolling, the machine places thin chocolate batons or a measured dollop of almond paste along the base of each triangle. The filling line operates with the precision of a printing press, dropping identical portions at high speed. The rest of the dough wraps around them seamlessly, encasing the filling without bursting the layers. After shaping, the croissants rest on trays or conveyor racks that move toward the proofing chambers. These are warm, humid rooms that mimic the gentle conditions of a traditional bakery, but on an industrial scale. Inside, the temperature sits around 27 degrees Celsius, with humidity near 80%. Over the next 45 to 90 minutes, the yeast gets to work again. Each croissant swells as gas pockets expand between the butter layers. The smell here is intoxicating. Butter, sugar, and yeast mingling into something unmistakably pastry-like. Proofing is a fragile stage, too short, and the croissants bake dense and heavy, too long, and they overexpand, bursting during baking. Computers monitor the chambers constantly, adjusting airflow and humidity in real time. Infrared sensors scan the trays, measuring surface growth and evenness. When the data shows the exact rise in volume, the trays move automatically toward the next step, baking. Before entering the ovens, the croissants pass beneath a misting station. A thin spray of egg wash, beaten yolks mixed with milk, coats the surface. This is what creates the iconic golden sheen and crisp exterior. The spray nozzles move back and forth in perfect rhythm, applying an even glossy layer. The air in this area smells rich and savory, the first hint of what's about to come. The ovens themselves are enormous tunnels, often over 20 meters long. Conveyor belts carry thousands of croissants through zones of precisely controlled heat. The first zone is hot, around 230 degrees Celsius, to trigger oven spring. The explosive expansion caused by steam from both the butter and dough. The next zones lower gradually, allowing the layers to set and brown evenly without burning. As the croissants bake, butter melts and vaporizes, forcing the dough layers apart into crisp, airy sheets. The factory fills with the unmistakable aroma of caramelizing butter and toasting flour, a smell that can travel hundreds of meters through ventilation ducts. By the time they exit the oven, the croissants are deep golden, hollow sounding when tapped, and flaky enough to shed crumbs even in the conveyor's motion. Cooling fans blast them with filtered air, stabilizing the crust and stopping the baking process instantly. The sound is like a soft rustle, a million tiny flakes settling at once. Some croissants are sold plain, while others continue to specialized lines for glazing or filling. For glazed versions, conveyors carry them under cascading curtains of apricot jelly, brushed thin for shine. For filled varieties, like custard or hazelnut cream, injectors pierce the base with tiny nozzles, depositing precise amounts into the center. Each injector operates under pressure, filling without collapsing the delicate interior. Once cooled, the croissants head for packaging. Robotic arms arrange them into rows, aligning the curved ends uniformly before feeding them into form and seal machines. Plastic films wrap around them, sometimes with nitrogen gas flushed inside to preserve freshness. The sealed packs move to labeling stations, where date codes and batch numbers are printed automatically. Each batch can be traced back to the exact moment it was mixed, proofed, and baked. For frozen croissants, common in large-scale operations, the process diverges just before baking. Instead of entering the oven, proofed doughs are quickly flash frozen at -40 degrees Celsius in spiral freezers. This locks in their structure, suspending yeast activity until baking. Bakeries and cafes around the world then bake them fresh on site, recreating the aroma and texture as if they'd just left the factory oven. A bagel begins its life as a lump of dense, sticky dough. Nothing elegant, nothing glossy, just raw potential waiting for transformation. Inside a modern bagel factory, the smell hits first. The sharp tang of yeast, the warmth of baked flour, and the faint sweetness of malt syrup hanging in the humid air. Around it all, machinery hums with steady rhythm. Mixers, kettles, conveyors, each one part of a process that turns those rough masses of dough into thousands of golden, chewy rings every hour. The process begins with flour. Strong, high-protein flour, the kind that can stand up to kneading and boiling without collapsing. Bagels demand structure, so the protein content hovers around 13 to 14%, higher than for most breads. From towering silos above the factory floor, measured streams of flour pour into giant horizontal mixers. Along with the flour comes water, yeast, salt, sugar, and, most importantly, malted barley syrup, which gives bagels their signature flavor and color. As the mixing starts, the dough fights back. It's stiff, resisting the machine's spiral arms, which churn and pull against it with deep, rhythmic groans. The resistance is intentional. Bagel dough uses less water than ordinary bread, creating a low hydration mix that bakes up dense and chewy rather than light and fluffy. Inside the bowl, friction from the metal beaters raises the temperature, warming the yeast just enough to wake it up. After about 10 minutes, the dough forms a heavy, elastic mass that stretches but doesn't tear, a living, breathing network of gluten strands. Once mixed, the dough is tipped out onto a conveyor and divided into massive blocks that rest under plastic covers. This rest period, called floor time, allows the gluten to relax and the yeast to begin fermenting. It's here that flavor begins to build. Even in a factory, the process can't be rushed. The dough needs time for the yeast to produce tiny bubbles of gas and faintly sour notes that will deepen during baking. The air in this section of the plant smells unmistakably like a bakery. Warm, doughy, and slightly sweet. When the dough is ready, it moves to the divider. This machine cuts the heavy blocks into smaller portions, each the exact weight of a finished bagel. Precision here is key. Even a few grams difference would cause uneven baking later. From the divider, each portion passes into a former, a set of rotating drums that shape it into a smooth cylinder, then poke a hole through the middle and seal the ends together. It happens so fast that the human eye can barely catch it. A raw bagel, perfectly round and uniform, drops onto a conveyor every half second. Older methods formed bagels by hand, rolling the dough into ropes, twisting, and joining the ends. But in a modern plant, the process has been mechanized to stunning precision. Still, the principle is the same. That central hole isn't decoration. It's functional, allowing the bagel to cook evenly when boiled and baked, and letting heat penetrate quickly in the oven. The freshly formed bagels now travel slowly on conveyor trays toward the fermentation room. Here the air is warm and moist, typically around 30 degrees Celsius with 70% humidity. The dough proofs gently for about 20 to 30 minutes, enough for the yeast to puff it up slightly, but not enough to turn it fluffy. Bagels are meant to be firm, not airy, and the factory controls this by limiting fermentation time. Sensors monitor the temperature constantly, while cameras track the rise of each batch. After proofing, the trays glide towards one of the most distinctive stages in the process: boiling. This is what separates bagels from all other breads. At the heart of the factory, massive kettles simmer with water infused with barley malt and a touch of sugar. Steam rises in fragrant clouds, and workers in protective aprons monitor the rolling bubbles. The proofed bagels slide down metal chutes into the water, bobbing like small buoys. They stay submerged for less than a minute, just long enough for the starches on the surface to gelatinize. This boiling step locks the crust, sealing in moisture and giving bagels their signature chew. Some factories use conveyor kettles, long troughs of hot water with moving mesh belts that carry the bagels through automatically. The sight is hypnotic. Hundreds of pale rings drifting through shimmering heat, their surfaces turning slick and glossy. When the bagels emerge, they're slightly puffed, firm to the touch, and ready for toppings. Wet surfaces are ideal for adhesion, so this is the perfect moment for flavor coatings. The freshly boiled bagels pass under rotating drums that shower them with sesame seeds, poppy seeds, dehydrated onion flakes, or coarse salt. For everything bagels, multiple topping feeders align in sequence, releasing their ingredients in overlapping bands. Each sprinkle is calculated to the gram. Cameras and weight sensors verify coverage. Too few seeds, and the bagel looks bare. Too many, and they'll burn in the oven. The topped bagels then head for the ovens. Industrial bagel ovens are enormous tunnel systems, some stretching more than 20 meters long. The first zone blasts intense heat over 250 degrees Celsius to trigger oven spring. Steam nozzles inject bursts of moisture to help the crust develop its signature shine. As the bagels move deeper, the temperature gradually lowers to bake the interior evenly without burning the seeds or toppings. The smell at this point is intoxicating. Roasted malt, caramelized sugar, and nutty flour blending into something unmistakably New York style. The bagels roll out of the oven in golden rows, their crust firm but still slightly pliable. Cooling conveyors carry them upward in looping spirals, allowing air to circulate evenly for about 20 minutes. This cooling phase is crucial. Too fast, and the crust wrinkles. Too slow, and condensation makes them soggy. The sound in the cooling area is a soft, rhythmic whisper, fans humming, conveyors rattling lightly, and the occasional crackle of crust settling as they cool. If the factory produces sliced bagels, they pass through slicing machines once cooled. The bagels ride along upright conveyors where spinning blades split them almost, but not completely, in half. Laser sensors align each cut to the bagel's natural seam, minimizing crumbs and keeping the halves attached for packaging. In some lines, bagels are then toasted lightly for pre-baked versions sold in frozen form. For fresh bagels, the journey continues directly to packaging. Robotic pickers, grippers fitted with soft silicone pads, lift and group them into neat stacks. Every dozen bagels form a perfect ring of golden crusts, ready for wrapping. Bags descend from automated rollers, filling and sealing with quick bursts of compressed air. The warm bagels disappear inside clear plastic, the smell sealed in just before it escapes. Each package receives a printed label with date codes, batch numbers, and timestamps, linking it back to the exact flour lot and mixing cycle. The entire process, from mixing to packaging, happens in less than 3 hours. Yet every step balances chemistry and craft. Bagel dough, though simple, behaves differently from any other bread. Its low hydration and boiling stage create a dense crumb, while the malt sugars caramelize during baking to give that deep brown crust. Factories maintain tight control over every variable: the pH of the water, the protein content of the flour, the concentration of malt syrup, even the mineral hardness of the local water supply. Every detail affects chewiness and color. Automation doesn't eliminate artistry, it refines it. Skilled operators know by sight and sound when something's off. They can tell from the sheen of the boiled bagels whether the water temperature has dipped, or from the smell of the ovens whether the malt syrup ratio needs tweaking. Computers might run the line, but humans keep its rhythm steady. In larger facilities, production never stops. Mixing, proofing, boiling, and baking run in a continuous loop, 24 hours a day. When one batch enters the oven, another is being shaped, and another is fermenting quietly in the warm air of the proofing room. The plant moves like a heartbeat, steady, cyclical, alive. By the time one shift ends, another takes over without pause, and the bagels keep rolling forward, endlessly. For frozen bagels destined for supermarkets, there's one more step: rapid freezing. After cooling, the bagels enter spiral freezers, where chilled air at minus 40 degrees Celsius circulates in powerful gusts. Within minutes, the moisture inside crystallizes uniformly, preserving the chew and preventing ice buildup. From there, they're sealed in bulk cartons and stored in vast cold rooms, stacked high like golden rings, suspended in frost. A muffin begins not with sweetness, but with sound. The deep, rhythmic churn of an industrial mixer. Inside a muffin factory, stainless steel paddles fold thick batter that glistens under fluorescent lights. The smell is warm even before the ovens start. Butter, sugar, and vanilla drifting through the air in soft waves. It's easy to forget, standing there among conveyor belts and cooling racks, that each simple, golden muffin represents a feat of controlled chemistry and industrial artistry. It starts, as all baking does, with ingredients, but here they arrive by the ton. Silos outside the factory hold fine wheat flour that pours into the production line through pneumatic pipes measured by weight sensors down to the gram. Nearby, liquid sugar and vegetable oil are stored in massive heated tanks, while refrigerated containers hold eggs, milk, and butter. Every ingredient is checked for temperature and consistency before it's allowed into the mix. The goal is uniformity. Every blueberry, every crumb, identical across millions of muffins. The process begins in mixing rooms where large spiral mixers, some capable of handling over 500 kilograms of batter at a time, wait beneath ingredient feeders. The order of addition matters more than most realize. First comes oil or butter, then sugar, which dissolves into it to create a smooth base. Eggs and milk are pumped in next, blending until glossy. Then the dry mix, flour, baking powder, salt, and sometimes a pinch of cornstarch, is sifted in gradually. As the paddles turn, the mixture thickens into the dense, rich batter that defines a muffin. Unlike bread, muffin batter isn't needed to build gluten. In fact, too much mixing would ruin it, making the final texture rubbery instead of tender. Modern machines solve this by using slow, folding paddles that mimic a baker's hand movements. Sensors monitor torque resistance inside the bowl, stopping the mixer automatically the moment the batter reaches perfect viscosity. The result is a smooth, velvety mixture that still holds air bubbles for lift during baking. Once the base is ready, it's time for flavor. Blueberry, chocolate chip, banana nut, double chocolate, each has its own sideline. Through insulated pipes, fruit purees, chocolate drops, or nut pieces are added in precise quantities. High-speed agitators fold them gently to prevent crushing or melting. In blueberry muffins, the berries are often frozen when added. This keeps them intact and prevents the batter from turning purple. Factories even use vibrating screens to separate clusters of berries before mixing, ensuring perfect distribution in every bite. The finished batter flows toward the depositing machines, and this is where the production floor comes alive. Long conveyor belts carry endless rows of paper baking cups that drop neatly into metal trays. Above them, piston depositors pump out exact portions of batter, each a perfect mound, neither too high nor too shallow. These machines work faster than the eye can follow, filling hundreds of molds every minute, each portion within a fraction of a gram of target weight. The smell here is sweet and slightly raw, like cookie dough warmed by friction. Operators in white coats monitor flow rates and cup alignment, adjusting valves and checking viscosity. If the batter thickens over time, a natural effect as air bubbles expand, temperature-controlled jackets around the pipes keep it stable. Every movement is designed to preserve uniformity, because uneven batter means uneven muffins. And that's unacceptable at scale. Once the trays are filled, they pass through a final inspection line. Cameras check that every cup has been filled evenly and that no drips or spills mar the tray. Any flawed portions are rejected automatically, scraped away, and recycled into the next batch. Then the trays disappear into the heart of the operation. The ovens. Industrial muffin ovens are tunnel-like giants, sometimes stretching the length of a bus. Inside, radiant heat and convection airflow combine to bake thousands of muffins at once. The first few minutes are crucial. The batter expands quickly as the water inside turns to steam, pushing against the gluten structure and lifting the dome. In a matter of minutes, the tops crack and rise, forming that familiar golden crown. Steam nozzles near the oven entrance inject controlled bursts of moisture, ensuring the muffins rise smoothly without splitting. The aroma that fills the air here is intoxicating. Sweet butter mingled with caramelizing sugar and a faint edge of vanilla. Workers walking by pause without meaning to, their clothes absorbing the scent. It's the smell of warmth itself. Inside the oven, temperatures start high, around 220 degrees Celsius, then drop gradually through the tunnel to finish baking the interior without drying it out. By the time the trays emerge at the other end, the muffins are fully set, their tops burnished to shades of amber and chestnut. Cooling is next, and it's just as important as baking. The trays roll onto spiral conveyors that wind upward through towers of circulating air. This allows the muffins to cool evenly over 20 minutes, avoiding condensation that would soften their crusts. The gentle hum of fans fills the air, and the muffin's faint crackling can be heard as the tops settle and shrink slightly. The structure is stabilizing, moisture redistributing from crumb to crust, a quiet, invisible process that determines freshness and texture. Once cooled, the muffins are either left in their paper cups or removed, depending on the packaging style. For wrapped muffins, robotic grippers lift them delicately onto parallel conveyors leading to the packaging area. The packaging room is cooler and drier than the rest of the plant. Humidity control is critical to prevent stickiness. Here, muffins destined for individual wrapping enter flow wrapping machines. Plastic film unwinds from massive rolls, forms around each muffin, and seals instantly with a thin line of heat. Nitrogen gas may be puffed inside before sealing, replacing oxygen to preserve freshness and prevent mold. Multi-packs follow a similar path, but are grouped in clusters before wrapping. Machines sort by weight, ensuring that every pack contains identical muffins with matching domes and color. Those intended for supermarket display might be sealed in clear trays with domed lids to protect their shape, while food service batches are bulk packed into lined boxes for cafes and bakeries to finish fresh on site. The entire packaging line operates with mesmerizing precision, conveyors gliding, sealers flashing, robotic arms stacking and boxing. Each bag or tray receives a printed label containing the batch code, oven number, and exact time of production. From there, pallets of warm, wrapped muffins roll toward the shipping docks, bound for distribution centers across the region. For frozen or par-baked muffins, common for export, the process changes slightly. Instead of cooling to room temperature, the trays enter blast freezers immediately after baking. Air at -40 degrees Celsius circulates at high speed, freezing each muffin within minutes and locking in moisture. These frozen muffins will later be thawed and finished in bakeries or hotels, smelling freshly baked even weeks after production. Behind the automation, the science of muffin making is all about balance. Each element, fat, sugar, leavening, flour, affects the final texture. Fat coats flour proteins, limiting gluten formation and keeping the crumb tender. Sugar draws in moisture, helping the muffins stay soft even after cooling. Baking powder and soda release carbon dioxide in two waves. First when mixed, then when heated, giving rise and fluffiness. Temperature, however, is the ultimate master. A shift of even 5 degrees can mean the difference between domed perfection and sunken tops. Factories fight constantly against those tiny variations. Air conditioning keeps the mixing rooms between 18 and 20 degrees Celsius year-round. Liquid ingredients are preheated in winter and chilled in summer to maintain consistency. Even the fruit is conditioned. blueberries stored at exactly -1 degrees to keep them firm. Chocolate chips kept in coolers so they don't melt before mixing. The result is mechanical perfection that still somehow feels handmade when you peel back the paper and break into one. It all begins, unsurprisingly, with flour. Krispy Kreme uses a proprietary blend of enriched wheat flour, one formulated specifically for its lightness, protein balance, and ability to yield that signature fluffy bite. The flour is sourced from select mills that maintain tight quality control standards, ensuring the particle size, protein content, and gluten strength all fall within strict tolerances. Once delivered to the facility, the flour is stored in stainless steel silos under controlled temperature and humidity, preventing clumping and spoilage. Next, there's yeast, the biological engine behind the dough's rise. Krispy Kreme uses a commercial strain of baker's yeast known for its rapid activation, consistent fermentation profile, and neutral flavor. The yeast is usually delivered in refrigerated blocks or vacuum-sealed pouches to ensure maximum viability. Alongside the yeast, the other raw ingredients include non-fat dry milk powder, high-stability vegetable shortening, dextrose, salt, and water. Each of these ingredients plays a crucial role in shaping the final taste and texture of the donut. The shortening provides mouthfeel and moisture retention, while the dry milk lends a creamy undertone and enhances browning during frying. In the mixing phase, the ingredients are loaded into a spiral or planetary industrial mixer. The water is typically warmed to around 95 to 105 degrees Celsius before being introduced to activate the yeast. The mixer operates on a timed cycle, first gently combining the dry and wet components, then increasing speed to develop gluten and build dough structure. The dough is mixed until it achieves a smooth, elastic consistency with careful monitoring of temperature and hydration levels. If the dough becomes too warm, it risks overproofing, too cold, and fermentation is delayed. Sensors in the mixing bowl monitor the dough's internal temperature, moisture content, and even CO2 output to ensure consistency. Once the dough is formed, it enters the bulk fermentation phase. Giant stainless steel troughs, called dough rests, hold the dough as it ferments for the first time. During this period, the yeast metabolizes sugars and starches, producing carbon dioxide and ethanol. This expands the dough and begins developing its light, spongy structure. Krispy Kreme controls this step precisely, maintaining a temperature of around 80 degrees and 85% relative humidity in the proofing room. The dough rests here for approximately 30 to 40 minutes, depending on the batch size and ambient conditions. After bulk fermentation, the dough is transferred to a sheeting system. This is where things start to get visually impressive. The dough is rolled and flattened by calibrated rollers until it reaches a uniform thickness, typically between 10 to 12 millimeters. From here, it enters the cutting stage. A rotary die cutter stamps out perfect donut rings and holes in a continuous, automated process. The cutting dies are precision machined from stainless steel to ensure sharp, clean cuts and minimal dough waste. Any scrap dough is immediately collected by conveyors and reintroduced into the mixing system for reuse. Each donut ring now travels along a conveyor to the second proofing chamber, essentially a gigantic, climate-controlled cabinet lined with slow-moving racks. Inside, the donuts undergo their final proof, where they double in size due to continued yeast activity. The environment here is tightly regulated, around 90 degrees here and nearly 85% humidity. This proofing process typically lasts 30 minutes, but sensors embedded in the chamber walls adjust for ambient shifts in temperature or humidity, ensuring each donut achieves the perfect rise. Now comes one of the most mesmerizing parts of the process, the fry line. The fully proofed donuts are gently deposited into a continuous flow fryer using an overhead lifting mechanism that preserves their delicate structure. The frying oil, usually a high-stability palm or soybean blend, is maintained at a precise temperature of approximately 365 degrees. Each donut floats along the surface, first frying one side, then automatically flipping at the midpoint using a mechanical turner. This results in the even golden brown exterior Krispy Kreme is known for. with a pale, proof line around the center indicating proper fermentation. The frying process takes just under a minute per side, and the timing is crucial. Over-frying results in a dense, oily product. Under-frying leaves it doughy and structurally unsound. Oil filtration systems continuously clean and circulate the frying oil, removing carbonized particles and extending the oil's life while maintaining food safety. Once the donuts exit the fryer, they move onto a draining conveyor where excess oil drips away. The donuts are now fully cooked, but they're still bare, until they pass through the glaze waterfall. This is the stage most visitors at Krispy Kreme stores eagerly watch through the viewing window. The glaze itself is a proprietary blend of confectioner's sugar, water, and stabilizers, mixed in large heated vats to maintain fluidity. It's heated to a precise temperature to ensure it flows evenly over the donuts without soaking them. As the donuts travel beneath the waterfall, a curtain of glaze coats their entire surface in one smooth motion. The donuts continue to move along the belt for several feet to allow the glaze to set. During this time, cooling fans blow across the surface to speed up the crystallization process, giving the glaze its characteristic sheen and snap. At this stage, the original glazed donuts are complete, but not all donuts stop here. Many are diverted down alternate lines for filling, topping, or decoration. Filled varieties like custard, jelly, or cream-filled donuts are processed using pneumatic injection stations. The donuts are gripped and punctured automatically, and then a precise quantity of filling is injected into each center using calibrated nozzles. Topping lines include various enrobing stations for chocolate dips, icing drizzles, and even cookie crumb coatings, depending on the product line. Once decorated, the donuts pass through a final quality control checkpoint. Here, high-speed cameras, sensors, and human inspectors work in tandem to identify deformities, glaze coverage issues, or structural flaws. Any donut that doesn't meet the company's stringent standards is diverted and discarded or sent for animal feed, depending on local regulations. Now comes the packaging process. Original glazed donuts are usually arranged by robotic arms into branded trays or boxes, depending on the sales channel, whether destined for in-store display, grocery retail, or food service distribution. Boxes are barcoded, date-stamped, and sealed automatically. For freshness, Krispy Kreme relies on just-in-time manufacturing. Many facilities bake and ship multiple times per day, with some outlets even co-located within the production plant itself to reduce handling and delay. For external distribution, the boxed donuts are loaded into climate-controlled trucks equipped with racking systems that prevent damage during transit. These trucks make scheduled routes to retail locations, grocery partners, and kiosk outlets, often arriving just hours after the donuts were made. Once on site, employees stock the shelves or display racks, ensuring the donuts are sold within their optimal freshness window, typically less than 24 hours. Meanwhile, any donuts not sold by the end of the day are generally removed to preserve Krispy Kreme's reputation for freshness. In some regions, unsold inventory is donated to food banks or repurposed, while others adhere to strict disposal policies. Throughout this entire process, automation and precision engineering play a central role. From programmable logic controllers managing the mixing and proofing cycles, to machine vision systems inspecting glaze coverage, every step is optimized for consistency, safety, and speed. The machinery involved is custom designed, often proprietary, and requires teams of trained technicians to maintain. Clean-in-place systems are installed throughout the facility to sanitize pipes, mixers, glaze troughs, and conveyors between production runs. This minimizes downtime while ensuring compliance with food safety regulations. Every aspect, from microbial swab testing to allergen control and traceability, is monitored via centralized software platforms, which can track each batch of donuts from flour silo to store shelf. The story of every M&M starts with one essential component: chocolate. The heart of a standard M&M is a solid drop of milk chocolate, though other varieties, like peanut, almond, crispy, pretzel, or peanut butter, feature different cores. But regardless of the variety, the production begins in the chocolate refining department, where raw ingredients such as cocoa liquor, cocoa butter, sugar, and milk solids are blended to make a smooth, consistent chocolate base. The chocolate used in M&Ms is tailored for firmness and melt resistance, specifically engineered to maintain its structure during the coating process. Large stainless steel tanks are used to melt and hold the chocolate at controlled temperatures. Automated valves and mixers regulate temperature, viscosity, and flow characteristics. Chocolate destined for M&M production must be carefully refined to reduce particle size, usually to around 20 microns. This is done in multiple stages using equipment like ball mills, roller refiners, and conches. These machines apply friction, pressure, and shear force to break down the solid particles until the chocolate achieves its desired mouthfeel. Once refined, the chocolate is pumped to depositors, automated nozzles that precisely dispense the liquid chocolate into molds or droplet-forming equipment. For the classic M&Ms, the chocolate is dropped onto a cool, rotating belt in small, round portions, forming button-shaped discs. These droplets are cooled rapidly using chilled air tunnels to harden them before further processing. The cooled chocolate centers are then collected and sent to the coating drums. These are large rotating pans, sometimes referred to as dragees pans or coating kettles, where the hard candy shell is gradually built around the chocolate core. This is the heart of the M&M production process and one of the most visually striking steps in the factory. The coating process is a slow and incremental buildup, achieved by spraying a fine mist of sugar syrup onto the tumbling chocolate centers, then drying and hardening that layer before repeating the cycle. Each coating drum can hold hundreds of thousands of chocolate centers at once. As the drum rotates, a fine spray of syrup, consisting mainly of sugar and water with optional corn syrup, is applied in short bursts. Warm air is then blown into the drum to dry the layer, allowing the sugar to crystallize into a thin, hard shell. This cycle is repeated dozens of times, each time adding a microscopically thin layer to build up the final shell thickness. Over time, this layering transforms the centers from soft chocolate buttons to perfectly round, hard-shelled candies. During this stage, technicians monitor coating uniformity, size consistency, and drying times using high-speed cameras and inline sensors. If the temperature or humidity in the coating room deviates too far from spec, it can ruin an entire batch, leading to shell cracking or poor adhesion. Once the desired shell thickness is achieved, the M&Ms are polished to give them their signature shine. This is done by adding polishing agents, such as carnauba wax or beeswax, to the coating drum in very small amounts. These natural food-grade waxes help create a glossy finish that not only enhances visual appeal, but also helps prevent sticking and moisture absorption during storage. The polishing phase takes less time than coating, but must be precisely timed to avoid over-waxing, which can result in a greasy or smeared appearance. The next step is color application, which may seem simple, but is, in fact, a carefully controlled phase. M&Ms come in a variety of colors, typically red, orange, yellow, green, blue, and brown. The color coding is applied using a sugar-based dye solution, sprayed in another round of layering inside rotating pans. Each batch is divided according to how many of each color are required. Food-grade colorants are mixed with water and a binding agent to ensure even adherence to the existing shell. After the colorant is applied, warm air is used to dry the layer, and another wax polish may be added to lock in the color and maintain shine. The factory uses precise batch tracking and automated scheduling software to ensure the correct number of each color is produced. For example, if red accounts for 20% of a standard bag's color distribution, the system ensures exactly that percentage is created during the run. This attention to detail keeps the consumer experience consistent across bags, boxes, and geographic regions. After color coding, the candies proceed to the printing station, where the iconic M is stamped on each piece. This is accomplished using high-speed, food-safe ink printers. The M&Ms are gently vibrated into a single layer on a moving conveyor belt that aligns them properly for stamping. The white edible ink is applied using a flexographic or offset stamping mechanism that imprints the M logo without damaging the candy surface. To ensure accuracy, machine vision systems monitor the printing in real time, checking for clarity, alignment, and completeness. Any candies that are misprinted or blank may be removed by pneumatic air jets and diverted for recycling or reprocessing. Now the M&Ms are ready for packaging. This phase of production involves a combination of robotics, weight-checking systems, and packaging machinery that operates at astonishing speeds. The candies are directed into vertical form-fill-seal machines or horizontal flow wrappers, depending on the packaging format. Multi-head weighers dispense precise quantities of M&Ms into each bag or pouch, ensuring weight compliance to legal standards. The packaging film is heat-sealed to form a tamper-evident, airtight barrier that preserves freshness and extends shelf life. For bulk formats, such as large tubs, party-sized bags, or vending packs, the process is slightly different but still highly automated. The machines are programmed to handle various product sizes, materials, and pack types without compromising accuracy. Barcodes, expiration dates, and lot numbers are printed onto each package to allow for traceability. Once packaged, the products are conveyed to case packing robots, which group them into cartons or boxes for shipping. These cases are then sealed, palletized by robotic arms, and shrink-wrapped for transport. Pallets are stored temporarily in climate-controlled warehouses before being loaded onto distribution trucks that carry them to retail centers, convenience stores, vending machine suppliers, and international shipping hubs. Throughout the entire process, food safety and quality control are paramount. The factory floor is governed by strict hygiene protocols. Employees are required to wear sanitary gear, and the equipment is sanitized regularly using automated clean-in-place systems. Random sampling is conducted at every critical control point, from chocolate refining to shell thickness to final packaging. Laboratory testing checks for microbial contamination, allergen presence, and chemical composition. Quality assurance teams also perform taste tests, structural integrity tests, and heat resistance trials to ensure the product meets Mars Inc.'s global standards. In the case of peanut or almond M&Ms, the process is similar but begins with nut preparation. Peanuts, for instance, are roasted in-house to develop their flavor and reduce microbial load. They are then cooled, sorted by size, and coated in a preliminary layer of chocolate before undergoing the same sugar shell layering process. Their irregular shape requires adjustments to coating speed and rotation patterns to ensure even coverage. The engineering behind M&M production is not only a marvel of food science, but also a study in high-speed manufacturing. Thousands of M&Ms can be produced every minute, yet each one must look and taste exactly the same. This requires the coordination of multiple disciplines: mechanical engineering, chemistry, automation, logistics, and sensory evaluation. The process begins not with whole potatoes, but with dehydrated potato flakes and potato starch. These form the base of the Pringles dough. The flakes are manufactured off-site through a separate drying process where peeled, cooked potatoes are mashed and then passed through drum dryers to remove water, creating thin, crisp sheets of dried potato. These are ground into fine granules and delivered to Pringles production facilities in bulk quantities, stored in climate-controlled silos to maintain moisture levels and prevent clumping. To this potato base, manufacturers add a precise blend of rice flour, corn flour, and wheat starch. This multi-starch formula gives Pringles their distinctive light, yet durable crunch, firmer than a classic chip, but less dense than a cracker. Each ingredient is selected for its functional properties. Rice flour contributes to lightness and reduces oil absorption. Corn flour provides structure and contributes to the crisp texture. Wheat starch acts as a binding agent and helps form the dough into a cohesive sheet. Inside the factory, these dry ingredients are metered into high-capacity industrial mixers. Water is added gradually, and the mixture is agitated until a cohesive dough forms. The consistency of the dough is critical. It must be pliable enough to be rolled and shaped, yet stiff enough to hold its form during frying. Too much water would cause the crisps to bubble and deform. Too little, and they would crack or crumble during processing. After mixing, the dough is conveyed onto a series of steel rollers in a sheeting machine. These rollers press the dough into a continuous, thin sheet, typically about 0.7 to 1 millimeter thick. The uniformity of this sheet is crucial, as even slight thickness variations can affect how the chips fry, blister, and brown. Advanced sensors mounted near the rollers continuously monitor sheet thickness, feeding data to the control system, which makes micro adjustments in real time. Next, the sheeted dough passes under a rotary die cutter. This is a cylindrical cutter with thousands of identically shaped molds engraved into its surface. As the sheet moves beneath it, the die cuts out dozens of curved oval crisps at a time, each one precisely measured to match Pringles' iconic dimensions, around 6.5 centimeters long and 5.5 centimeters wide, shaped with a unique double-curved profile known as a hyperbolic paraboloid. This mathematical shape isn't just aesthetic, it offers stackability, strength, and an audible crunch due to its uniform stress distribution. The dough scrap that remains between the cutouts is immediately separated and returned to the beginning of the process. Conveyor belts collect and transport the unused dough back to the mixer, where it is reincorporated into fresh dough. This closed-loop system minimizes waste and ensures efficiency in ingredient usage. Once cut, the raw crisps are gently lifted from the sheet using suction cups or air jets and placed onto a moving metal belt composed of dozens of concave molds. Each mold perfectly matches the chip's final saddle shape. This belt then moves the raw crisps into the fryer, an enormous stainless steel bath filled with hot vegetable oil, maintained at a consistent temperature of around 170 to 180 degrees. The crisps are submerged for approximately 11 seconds, long enough to remove moisture and induce a Maillard reaction, giving them their light golden brown hue and toasty flavor. Unlike traditional deep-fried potato slices that can curl, bend, or form bubbles, the Pringles molds maintain each crisp's structure during frying. Because the crisps are uniformly thin and precisely shaped, they fry evenly with no dark spots or oil saturation. Excess oil is quickly removed as the crisps exit the fryer and pass over a series of vibrating conveyors and air knives, high-pressure jets that blow away any surface oil or crumbs. At this point, the freshly fried crisps are hot, dry, and unseasoned. They move into the seasoning tunnel, a long, rotating drum equipped with sprinklers or spray nozzles. Here, flavor powders, ranging from classic original to sour cream and onion, cheddar cheese, or barbecue, are evenly applied as the crisps tumble and rotate. The flavor powders are formulated to stick to the crisp's surface via residual oil left from frying. In some varieties, additional ingredients such as powdered cheese or dehydrated vegetables are included in the seasoning blends. To prevent flavor loss and preserve freshness, the seasoned crisps are quickly cooled using forced air systems before entering the packaging phase. This cooling is critical. If the crisps are too warm, condensation can form inside the package, leading to soggy chips and microbial risk. Once cooled, they are conveyed to the stacking and canning line. This is where another defining feature of Pringles becomes prominent: their tubular canister. The stacking machine uses a system of synchronized mechanical arms, optical sensors, and robotic paddles to stack crisps one by one into perfectly aligned columns. This process is remarkably fast and precise. A sensor verifies each crisp's shape and orientation before it's inserted into the growing stack. Once a full stack reaches the correct height, typically around 80 to 100 crisps, depending on the packaging size, it is inserted vertically into a cardboard can that's been pre-formed and lined with a metallized film to prevent oil seepage and moisture intrusion. Each can is equipped with a plastic bottom, which is ultrasonically welded or heat sealed in place before filling. After the crisps are inserted, a foil lid is applied and hermetically sealed using induction heat or pressure bonding to ensure an airtight closure. A plastic snap-on cap is then placed on top, providing resealability for consumer convenience. The filled cans are then labeled and date-coded. Each can receives a printed batch number and expiration date to ensure traceability throughout the distribution chain. Vision inspection systems scan each can to ensure it is filled to the correct level, sealed properly, and free of any external defects like dents or mislabeling. Cans are grouped into multi-packs or cartons by robotic arms and placed on pallets for storage or shipment. Depending on demand and product line complexity, different varieties of Pringles may be produced in separate production runs on the same line, requiring quick and thorough cleanouts between batches to prevent flavor cross-contamination. From here, Pringles are shipped to distribution centers, retailers, and convenience stores across the globe. Thanks to the uniform shape and rigid packaging, they travel exceptionally well, with minimal breakage compared to traditional bagged chips. This durability, coupled with the brand's distinct identity, has made Pringles a staple in global snack markets. Sanitation and quality control are central throughout the process. Each stage of production, from dough mixing to final packaging, is monitored by automated control systems and human operators. Random samples are collected for lab analysis to check moisture levels, oil content, seasoning distribution, and texture. Microbial testing ensures no contamination occurs during handling. Metal detectors and X-ray machines inspect each can before shipping to catch any foreign objects that may have entered the line. Allergen controls are strictly enforced, particularly when switching between varieties like original and cheddar cheese. In addition to ensuring food safety, the factory design and equipment layout support continuous cleaning. Many machines feature clean-in-place systems that pump sanitizing fluids through the equipment without requiring disassembly. Air filtration systems and positive pressure rooms minimize the risk of dust and airborne contaminants affecting product quality. Beyond the manufacturing floor, the creation of new Pringles flavors and formats involves food scientists and R&D specialists who develop seasoning blends, test mouthfeel, and conduct sensory panels with trained tasters. Innovations like Pringles Wavy or Pringles Scorchin follow the same base process, with minor adjustments in dough formulation or seasoning protocols. Despite their high-tech origin, Pringles still deliver a simple satisfaction, a crisp, flavorful bite that feels familiar and fun. But behind that enjoyment is a complex dance of precision equipment, mathematical shaping, and carefully designed formulations. From powdered potatoes to perfectly stacked crisps, every Pringle is a product not just of flavor, but of industrial ingenuity, a testament to how food science can transform something as humble as a potato into a globally recognized snack. The production of Domino's pizza begins not in the store kitchens, but in massive regional supply chain centers, where the ingredients, particularly the dough, are produced in industrial quantities with an emphasis on consistency, quality, and efficiency. Before any pizza reaches the oven in a Domino's franchise, it starts its journey in these highly controlled factory environments where each element is formulated to exact specifications. The first and most critical component is the dough, which is made fresh daily in these centers and delivered under cold storage conditions to every Domino's outlet. The dough making process begins with the arrival of bulk ingredients, including high-protein wheat flour, water, vegetable oil, yeast, sugar, and salt. These ingredients are stored in separate storage systems based on their physical state and volume requirements. Flour is kept in massive silos connected to the production floor through pneumatic tubing systems. These tubes transfer flour directly into the industrial-scale mixers with precise weight measurements, controlled by automated batching systems. Water, which must be maintained at a specific temperature range to activate the yeast properly, is stored in stainless steel tanks connected to digital flow meters. This ensures the exact volume is dispensed into each batch, typically to within 1/10 of a liter. Vegetable oil, sugar, salt, and yeast are also dispensed through closed-loop systems that prevent contamination while ensuring high-speed delivery and accuracy. The industrial mixers used at this stage are horizontal, high-capacity spiral mixers or fork mixers, depending on the location and the specific equipment model in use. Each mixer is designed to handle hundreds of pounds of dough per batch, usually around 400 to 600 pounds. The process begins with dry ingredients being added first, followed by a controlled stream of water and oil. Once the mixture reaches the desired hydration point, the mixer operates at different programmed speeds to knead the dough until it reaches the correct elasticity and gluten development. This usually takes around 8 to 10 minutes, with temperature sensors embedded in the bowl to prevent overheating from friction, which can damage the yeast. As the dough mixes, factory floor operators monitor each batch's time, temperature, and consistency through a computerized interface. Every mixer is part of a larger manufacturing execution system that records batch data, ingredient lots, timestamps, and operator IDs. This traceability system ensures that if a problem ever arises, such as inconsistent rise or poor texture in a batch, managers can track it back to the specific flour lot or mixing time and make necessary adjustments for future runs. Once the dough reaches optimal consistency, it is automatically discharged from the mixer into a dough trough, which is essentially a wheeled stainless steel container that holds the dough until it's moved to the dividing station. The dough is then transferred into a hopper above a hydraulic or rotary dough divider. This machine uses either vacuum-assisted suction or mechanical cutting blades to portion the dough into uniformly weighted balls, typically ranging from 6 to 20 ounces, depending on the final pizza size. Each portion is measured by load cells, digital weighing systems that maintain accuracy within a few grams. These dough balls then proceed to the rounding machine, which takes each divided piece and rolls it into a tight, smooth sphere. This is crucial for creating the internal tension needed for a uniform rise during fermentation. The rounding machine uses rotating plates or belts that apply gentle pressure and a circular motion to the dough. After rounding, the dough balls are dusted lightly with food-grade flour or semolina to prevent sticking, and then placed into oiled dough trays. These trays are stacked and covered with plastic lids or wraps to maintain humidity and prevent surface drying. They're labeled with a printed barcode that includes the production date, time, dough type, and batch number. At this point, the dough enters the proofing phase, which is critical to developing both the structure and flavor of the final pizza base. Proofing occurs in temperature and humidity-controlled rooms, where racks of dough trays are stored for several hours. The ideal proofing conditions are generally around 80 degrees Fahrenheit with 75% relative humidity, although this can vary slightly based on factory location and yeast activity. The yeast begins to consume the sugars in the dough, producing carbon dioxide and ethanol as byproducts. This gas becomes trapped within the dough's gluten network, causing it to expand and develop the characteristic, airy, chewy structure. Simultaneously, organic acids and alcohols created during fermentation start to build complex flavor notes in the dough. During the proofing period, plant operators conduct regular checks to monitor dough expansion, surface tension, and even internal temperature using infrared thermometers and visual inspection. Some factories use automated camera systems that scan the trays and calculate proofing progress by measuring the dough's rise and dome shape. Any deviations from the standard profile are flagged for intervention, whether that means extending the proofing time or moving certain trays to a different section of the proofing room. Once the dough reaches the desired level of fermentation, it is moved to the cold storage phase. In this stage, the dough trays are rolled into large walk-in refrigeration rooms, where the temperature is maintained at approximately 2 to 4 degrees Celsius. This halts the yeast's activity and locks in the developed flavor while also preventing overproofing. The chilled dough can now be stored for up to several days, depending on demand at the destination stores. During this time, the trays are rotated to maintain even cooling and are occasionally inspected for signs of over-fermentation or drying. While the dough is being prepared, Domino's is also handling the sauce production in parallel. Tomato sauce is made in separate processing areas, using high-volume stainless steel kettles equipped with agitators and heating jackets. The base of the sauce is tomato paste, which is diluted with water to reach a specific consistency. To this, measured quantities of salt, sugar, oregano, garlic, basil, black pepper, and other proprietary spices are added. Some locations use pre-mixed spice sachets that are batch-coded for accuracy, while others blend the seasoning on site. The sauce mixture is heated to temperatures between 80 and 90 degrees Celsius to sterilize it and meld the flavors. Once the heating process is complete, it is rapidly cooled using a plate heat exchanger to bring it down to refrigerated storage temperature, usually 30 degrees Celsius, around 4 degrees Celsius. The cooled sauce is then transferred into food-safe storage containers, often in 10-liter or 20-liter units, and sealed with tamper-evident caps. Each container is labeled with a batch code and production date before being staged for shipment alongside the dough. In addition to sauce, the factory prepares other key ingredients, including shredded cheese and select toppings. The cheese used in Domino's pizzas is typically a low-moisture mozzarella, known for its excellent melting properties and stretch. Some supply centers receive the cheese in bulk blocks and shred it in-house using high-speed rotary shredders that slice the blocks into uniform strands. The shredding process includes a light coating of anti-caking agents like potato starch or cellulose to prevent clumping during storage. The shredded cheese is packed into portioned bags, vacuum sealed, and stored under refrigeration. Once all ingredients, dough, sauce, cheese, and prepped toppings are ready, they are organized and loaded into refrigerated delivery trucks. These trucks operate under a tight logistics schedule, making daily or multi-day trips depending on the volume needs of each Domino's franchise store. The internal temperature of each truck is continuously monitored using GPS-integrated data loggers, and real-time data is fed back to the supply center's central operations system. This ensures that if any deviation in temperature or route timing occurs, corrective action can be taken immediately. By the time the products arrive at the store, they are fully prepared and only require assembly and baking. The franchise stores then execute the final steps of pizza preparation, which involves pressing out the dough, saucing, topping, baking, and packaging. However, the factory's role is absolutely central to ensuring that every ingredient arrives at the exact same standard, no matter where the pizza is being made or consumed. Through this centralized and automated model, Domino's achieves consistency at a global scale, while minimizing waste and human error in the earliest and most foundational stages of production. Once the refrigerated trucks deliver the dough, sauce, cheese, and toppings to each Domino's franchise, the handling of those ingredients transitions from centralized factory production to carefully structured in-store processes that continue to follow standardized protocols. However, the factory's influence is far from over at this point. The store-level procedures are engineered to mirror the consistency, precision, and speed found in the supply chain centers, effectively extending the factory environment into each retail location. Inside the store, the first critical action is the proper storage of the dough. As the dough trays arrive straight from cold storage, they are transferred into the store's walk-in refrigerator, where they are kept at a consistent temperature of 2 to 4 degrees Celsius. Each dough tray remains sealed with its identifying barcode, which includes the production batch, date, and shelf life. This code is scanned upon arrival, logged into the store's inventory system, and linked to the store's daily forecast so the staff can prioritize older dough for earlier use, following a strict first in, first out system to ensure freshness and prevent waste. Before the dough can be used for making pizzas, it needs to temper. Cold dough straight from refrigeration is too stiff and contracted to stretch evenly or bake correctly. Therefore, several trays are pulled from the cooler in staggered intervals and placed in a proofing area within the store, typically kept at room temperature for 30 to 60 minutes. During this period, the dough relaxes, allowing the gluten to become more extensible and the yeast to reawaken slightly, which enhances browning and flavor development in the oven. This step also restores some of the softness and elasticity necessary for the dough to perform consistently on the preparation line. The next key phase in the process is dough pressing or hand stretching, which transforms the proofed dough ball into a pizza base. Depending on the store's equipment and regional preferences, Domino's uses one of several standard methods for this. In many high-volume locations, a mechanical dough press is employed. This press is a heated platen system where a single dough ball is centered between two metal plates. With controlled pressure and temperature, the plates compress the dough to the specified diameter and thickness. The brief heat exposure also helps to set the edge of the crust slightly, which prevents overexpansion during baking. Other stores use hand-stretching techniques, which involve manually flattening the dough using the palms and fingertips to create an even disc, often followed by a gentle spinning motion to widen it to the correct diameter. Employees are trained to feel for even dough resistance, check the uniformity of thickness, and ensure the edges are slightly thicker to create the signature Domino's crust ring. Some locations employ a dough sheeter, a machine that flattens dough between two adjustable rollers, which is commonly used for medium thickness crusts or thin crust options. Once the dough is properly shaped and placed on a pizza screen or baking tray, it is ready to be sauced. The sauce comes in pre-measured containers or large bag-in-box systems with pump dispensers, depending on the store's volume. A standardized rotary sauce ladle or domed saucer is used to apply a precise amount of sauce, usually between 90 and 120 grams for a medium pizza. The sauce is spread using a circular motion that stops approximately 1 inch from the crust edge to allow for natural bubbling and rim development during baking. With the base sauced, the next step is the cheese application. Domino's cheese is a proprietary, low-moisture mozzarella blend, optimized for melt, stretch, and browning. The cheese arrives shredded in sealed, chilled bags and is stored in under-counter refrigeration near the prep stations for quick access. Employees use color-coded scoops to portion out exact grams of cheese per pizza size: small, medium, large, or extra large. This consistency ensures that the cheese melts evenly and that the nutritional and caloric values remain standardized. In high-throughput stores, preloaded portion dispensers or weigh scales may also be integrated into the cheese station to reduce time and improve accuracy. Next, the pizza moves to the topping stage. Domino's toppings, such as pepperoni, Italian sausage, mushrooms, green peppers, onions, olives, jalapenos, grilled chicken, and bacon, are kept in ingredient rails with stainless steel pans, maintained at safe refrigeration temperatures using undermounted chillers. Each topping has a designated scoop or set of tongs, and employees are trained to apply the correct amount and distribution per pizza size and recipe. Toppings are applied in a set sequence to ensure even cooking and consistent flavor layering. For example, pepperoni slices are laid edge to edge to cover the surface in a signature circular pattern, while sausage crumbles are more scattered to allow airflow between pieces. Vegetables are typically added last, as their moisture content can impact the crispness of the crust if layered too deeply. Domino's uses laminated guides and portion charts to ensure that every pizza, regardless of who's preparing it, looks, weighs, and tastes the same. With the pizza fully assembled, it is placed onto a conveyor belt oven, also known as an impingement oven. This oven style uses jets of superheated air blasted from top and bottom to ensure even baking. The oven belt is set to a precise speed, generally resulting in a 5.5 to 7 minute bake time, depending on the pizza size and topping density. The oven's digital interface allows staff to select different profiles for thin crust, hand-tossed, deep dish, or extra cheese options. Each profile adjusts air velocity, top and bottom heat ratio, and belt speed to produce the ideal bake for that style of pizza. During baking, several chemical and physical transformations take place. The crust expands slightly. From the final stage of yeast fermentation, steam is released from the sauce and toppings, and the cheese melts and begins to brown through the Maillard reaction. Excess moisture from vegetables is evaporated by the oven's airflow, ensuring the crust remains crisp and doesn't sag. The pizza emerges from the other side of the oven, fully baked and ready for slicing. At the end of the conveyor, pizzas are transferred to a staging counter, where they rest for 20 to 30 seconds to allow the cheese to set slightly. Then, using a rocker blade or circular pizza cutter, employees cut the pizza into standard portions, usually 8 slices for a large pizza, based on Domino's cutting guides. Each pizza is then slid into a branded corrugated cardboard box, which is specially designed with vent holes and moisture-absorbing liners to preserve crispness during delivery. Every box is sealed and receives a printed label generated by the store's order management system. This label includes the customer's name, order number, timestamp, and pizza specifications. For orders placed online or through the app, this also triggers an update on Domino's proprietary pizza tracker, which uses real-time data from kitchen sensors to notify customers of each stage, from dough prep to oven entry, baking, boxing, and out for delivery status. Throughout the day, all these processes are monitored for compliance with Domino's global standards. District managers conduct regular audits using detailed checklists covering dough handling, oven cleanliness, bake quality, topping accuracy, and safety procedures. Additionally, Domino's has built-in kitchen timers and alert systems that ensure no dough is held at room temperature too long, no pizzas sit unboxed beyond the quality threshold, and no ingredients are used past their hold times. Each store's operations are built to match the precision and consistency of the supply chain factories. In fact, many stores undergo periodic retraining sessions to realign their practices with the upstream factory procedures. This ensures that no matter how far the finished product is from the centralized dough production, the final experience to the consumer remains nearly indistinguishable between one location and the next. As soon as a Domino's pizza is sliced and boxed, the journey continues into a carefully engineered phase focused on preserving product quality and maximizing delivery efficiency. At this point, what might appear to the customer as the simple act of putting a pizza in a box and sending it out the door is, in reality, a continuation of Domino's factory-grade systems, refined, tracked, and executed with industrial precision. Each Domino's box is made of specially designed corrugated cardboard, engineered not only to be structurally strong enough for stacking and transportation, but also to allow moisture control and thermal retention. Small vent holes are strategically placed around the box edges to allow steam to escape without sacrificing internal heat. This is critical to maintaining a crisp bottom crust while keeping the cheese and toppings hot and intact during transit. The liners inside some specialty pizza boxes also use grease-resistant coating and moisture-wicking micro layers that reduce sogginess, especially in pizzas with heavier vegetable or meat toppings. Once the pizza is placed in its box, a label is immediately printed and applied. This label contains all relevant details: the order number, pizza type, time of bake, the customer's name and address, and specific cooking instructions if applicable, like extra crispy crust, light sauce, or no cheese. More importantly, the label also includes digital timestamps and batch codes that tie the finished product directly back to every earlier phase of production. These codes link the order to its dough batch, sauce mix, cheese lot, and even the name of the employee who boxed it. This allows full traceability and in the event of a customer complaint or quality issue, managers can pull up detailed records to investigate and resolve the problem efficiently. The next link in the process is the delivery system, which Domino's has industrialized to a level similar to its supply chain and production operations. Every Domino's location uses a centralized digital system to optimize delivery routes, monitor driver location, and track pizza temperature using estimated time-to-door algorithms. In some urban areas or flagship locations, Domino's even uses thermal sensors and GPS modules in the delivery bags themselves. These sensors ensure that the pizza never drops below the acceptable temperature threshold, typically around 140 degrees Fahrenheit or 60 degrees Celsius, which maintains cheese integrity and topping stability. The delivery bags used are not basic insulated containers. They are purpose-built thermal sleeves with advanced insulation material, sometimes incorporating phase change materials that hold heat without overheating the product. These bags are lined with aluminum and closed with Velcro or zippers to ensure no heat escape. In some pilot programs, Domino's has experimented with electrically heated delivery pouches that plug into the vehicle's charging outlet, maintaining a regulated temperature across the entire delivery window, especially in colder climates. While the pizza is en route, Domino's proprietary pizza tracker remains active. This cloud-based interface receives inputs from multiple sources: the POS system, kitchen sensors, label printer, and delivery dispatch terminal, and creates real-time updates for the customer. As soon as the order is marked out for delivery, a countdown begins based on predictive delivery timing, factoring in distance, time of day, historical traffic data, and driver availability. This transparency not only improves customer satisfaction, but also provides performance data for internal use. Behind the scenes, Domino's aggregates all this operational data into their enterprise-wide performance dashboards. Each store's key performance indicators, such as order accuracy, delivery time, baking efficiency, and customer satisfaction scores, are updated daily. Store managers and regional supervisors review these metrics in regular meetings, identifying trends, deviations, and opportunities for improvement. If a certain franchise location consistently shows slower bake times or increased complaints about cold pizza, it may trigger a maintenance review of the oven system or retraining of kitchen staff. Meanwhile, at the supply chain level, Domino's uses reverse logistics to complete the factory-style loop. Once a delivery is completed, used ingredient bins, dough trays, and empty sauce containers are returned to the regional supply centers on the next inbound truck trip. These items are cleaned, sanitized, and reused according to food safety protocols. Reusable dough trays, for example, go through automated washing systems that use high-pressure jets, detergent, and thermal sanitation to prepare them for the next production cycle. By managing both outgoing and incoming flows efficiently, Domino's minimizes waste and maximizes logistical efficiency, keeping the system sustainable and cost-effective. Beyond the visible kitchen and delivery operations, there is also a sophisticated forecasting and inventory management system that relies heavily on factory data. Using AI and machine learning, Domino's forecasts demand for dough, sauce, cheese, and toppings at each store based on variables like local events, weather, historical order volumes, and even social media trends. This information is transmitted back to the supply chain centers, which adjust dough production and ingredient packaging accordingly. For example, if a city is expecting a snowstorm, the system may predict a spike in delivery orders and increase dough production by 10% for the affected stores. This tight integration between forecasting and factory production minimizes spoilage and overproduction, ensuring that only as much dough and sauce is produced as will be used within a defined freshness window. The same logic applies to toppings and cheese. Ingredients that are nearing the end of their shelf life can be flagged automatically, prompting store managers to run promotional offers or bundle deals to encourage faster turnover. By linking the retail environment back to the factory floor, Domino's achieves a level of responsiveness and precision rarely seen in traditional food service operations. Domino's also incorporates periodic updates and R&D feedback into its manufacturing systems. When a new product is launched, such as a specialty crust or a new line of toppings, the manufacturing centers adapt their formulations and packaging processes to accommodate the change. For instance, a new crust option may require a dough with a different hydration level or proofing profile. In that case, dough mixers are recalibrated, proofing room settings adjusted, and additional QA steps introduced. The product launch timeline includes upstream changes that affect every supply chain center, down to the labeling system and transport logistics. To maintain global brand consistency, Domino's has standardized its production protocols across all countries, yet also incorporates regional customization. For instance, the dough produced in India may include slight formulation changes to better suit local humidity levels or flour types. In Japan, where crust styles vary, dough mixing and resting procedures may be adapted for fluffier or rice-infused bases. However, the core manufacturing principles, precise batching, automated mixing, cold chain delivery, and digital inventory tracking, remain consistent regardless of geography. Domino's also performs routine auditing and calibration of their supply chain centers to ensure continued alignment with performance standards. Factory equipment such as mixers, dividers, and temperature control units are subjected to preventive maintenance and calibration checks at regular intervals. Technicians verify dough density, elasticity, and yeast activity using physical measurements and digital readouts. Similar checks are done for sauce viscosity, cheese fat content, and topping moisture levels. These numbers are logged and analyzed to identify any drift from target specifications, allowing corrective measures to be implemented before product quality is affected. Even packaging materials go through quality control. Corrugated boxes are tested for burst strength, fold endurance, and thermal retention properties. Adhesives used for box sealing are food safe and resistant to temperature extremes. The printing quality on labels is monitored to ensure clarity and durability, as these labels serve both customer-facing and internal traceability functions. Everything down to the ink used on packaging is selected for durability under heat and moisture, a testament to the factory-level thinking that permeates the entire Domino's ecosystem. It all begins with the peanuts. While it might seem obvious that a peanut butter cup would start with peanuts, what's not widely known is just how much control and specificity Hershey applies to this ingredient before it ever reaches the cup itself. Reese's production lines require massive quantities of peanuts, hundreds of tons per week across facilities, and not just any peanut will do. The factory demands high oleic runner peanuts, most commonly sourced from farms in Georgia, Alabama, and Texas. These peanuts are preferred for their uniform kernel size, mild flavor, and high oil content, which delivers a creamier peanut butter base. Once harvested, peanuts are sent to dedicated shelling and blanching facilities, where they are cleaned, sorted, and skinned. The outer red skins are removed through dry abrasion, and the kernels are visually and electronically inspected to eliminate any with defects, mold, or foreign materials. Only the highest grade peanuts, typically designated as US Fancy or US Extra Large, are accepted for Reese's production. These peanuts are then loaded into food-grade hoppers and shipped in sealed bulk containers to the peanut butter manufacturing lines at Hershey's centralized processing plants. Upon arrival at the factory, the peanuts are stored in stainless steel silos within a climate-controlled environment to prevent spoilage. Prior to use, the peanuts are metered into roasting drums. Roasting is a critical step not just for flavor, but for aroma development and moisture reduction. High-capacity rotary roasters or continuous conveyor-style roasters are used, depending on the factory's line design. Peanuts are typically roasted at temperatures between 320 degrees Fahrenheit and 360 degrees Fahrenheit for 30 to 45 minutes. The exact temperature curve is adjusted based on peanut moisture and oil content, which is sampled batch by batch in the factory's lab using gas chromatography and moisture analyzers. The roasters are equipped with air impingement systems and inline sensors to monitor internal temperature, color, and roast development in real time. At various intervals, small test samples are pulled using auto draws for taste panel review. Roast level has to be absolutely consistent, as this is the foundation for the signature Reese's peanut butter flavor. Over-roasted peanuts will produce a burnt or overly bitter taste, while under-roasting leaves the flavor bland and oily. Once roasted, peanuts are cooled using high-powered air chillers to prevent overcooking and to stabilize the oils. They are then conveyed into degermers and mechanical splitters, where they are cracked open and the hearts, the hard inner core of the peanut, are removed. These hearts, while technically edible, can impart a bitter or chalky aftertaste, so they are separated out and typically used in livestock feed or secondary food processing streams. Now comes the grinding phase. The roasted and cooled peanuts are fed into large, high-shear grinders, industrial versions of what's used in commercial peanut butter production. These grinders operate at extremely high RPMs and are often configured in a two-stage system: a coarse grind followed by a fine grind. In the coarse phase, the peanuts are broken down into a grainy paste, preserving small particulates that contribute to the slightly gritty texture of Reese's peanut butter. This paste is then piped into a second mill, where it's refined to a smooth, uniform consistency. The peanut paste is blended in stainless steel mixing tanks equipped with variable speed paddles and heated jackets. At this stage, a proprietary mix of additional ingredients is incorporated. These include salt, sugar, a small amount of fully hydrogenated vegetable oil, and a dry milk derivative. The sugar used is finely milled and sieved to a consistent particle size, ensuring it disperses evenly throughout the mix without recrystallizing. Emulsifiers such as mono and diglycerides are added in microdoses, enabling the fat and protein phases to remain homogeneous over time. What makes Reese's filling unique, and one of the factory's guarded secrets, is its texture. It isn't traditional creamy peanut butter. It's dry and crumbly, almost fudge-like, but melts smoothly on the tongue. This is achieved by very specific moisture and fat content targets. The factory carefully controls the fat ratio in the peanut blend using inline nuclear magnetic resonance sensors, which measure fat levels without destroying samples. The ideal balance results in a pliable, moldable filling that holds its shape during chocolate enrobing but softens under bite pressure. Once blended, the peanut butter filling is pumped into chilled hoppers and held at precise temperature, typically between 60 degrees Fahrenheit and 70 degrees Fahrenheit, so it can be extruded or deposited with exact weight and shape control. Temperature consistency is crucial here. Too warm, and the filling becomes too soft and spreads when deposited. Too cold, and it hardens and resists clean shaping, risking damage to the chocolate cup. The final stage in this first segment is the formation of the peanut butter centers. On a separate production line, the cooled peanut filling is portioned using servo-driven pistons or extrusion rollers, depending on the cup format being produced. These machines deposit small, perfectly measured mounds of filling onto a chilled conveyor. In larger cups, the filling is puck-shaped. In minis, it's closer to a small dome. Each peanut butter deposit is then transferred into a temporary holding tunnel, essentially a refrigeration corridor, where the shaped fillings are stabilized prior to the chocolate enrobing phase. Here, humidity and temperature are carefully balanced to avoid condensation or fat bloom when chocolate is later applied. At this point, the peanut butter centers are firm, uniform in size and shape, and fully ready for the next critical phase of the process, chocolate molding. With the peanut butter centers now precisely formed, cooled, and stabilized, the next critical phase in the industrial production of Reese's peanut butter cups begins: chocolate shell creation and cup assembly. This portion of the process is all about precision, timing, and the seamless integration of multiple complex systems to produce a product that's visually perfect and texturally balanced. It's here that the familiar cup shape begins to take form, and where Hershey's decades of manufacturing expertise are on full display. The chocolate used in Reese's products is developed in-house and differs slightly from that used in a Hershey's milk chocolate bar. While it still contains cocoa solids, cocoa butter, milk solids, sugar, and lecithin, it has been tailored specifically to pair with the salty sweet peanut butter filling. The chocolate is slightly softer in melt, less bitter than dark chocolate, and has a fat and sugar profile that ensures it doesn't overpower the filling. It's formulated to be both moldable and stable under typical shelf conditions, even in warmer climates. The chocolate arrives at the cup production line in a liquid state, held in large tempering tanks kept at a precise temperature, usually around 30 to 32 degrees Celsius for milk chocolate. Tempering is an essential part of chocolate manufacturing and involves heating the chocolate to fully melt its cocoa butter crystals, cooling it to initiate the formation of stable type 5 crystals, then gently reheating it to bring it to working temperature. This process ensures that once the chocolate is set, it has a glossy finish, resists bloom, and has a clean snap when broken. The first step in forming the Reese's cup is lining the signature brown paper cup mold with chocolate. The production line is fed with pre-formed paper cups stored in large reels or stacked columns that are automatically dispensed onto a high-speed conveyor. These paper cups are food-grade, waxed, or coated with a thin moisture barrier and shaped precisely to hold their structure during and after chocolate deposition. Once the paper cups are set in place on the moving line, a chocolate depositor head releases a measured dose of tempered chocolate into each one. This is known as the bottoming phase. The amount of chocolate is critical, not only for structure, but also for controlling the ratio of chocolate to filling. After deposition, the cups pass over a vibration table. This stage is crucial for evenly spreading the chocolate along the bottom and slightly up the sides of the paper cup. The vibration table uses rapid, controlled pulses to remove air bubbles and to ensure a uniform shell that won't crack or collapse during filling. Immediately following the bottoming step, the peanut butter centers are dropped into the liquid chocolate. These centers have been transferred from the refrigerated holding tunnel to the enrobing line and are picked and placed with robotic arms or pneumatic suction systems that gently lower each piece into its corresponding chocolate-lined cup. The timing of this placement is perfectly synchronized so that the peanut butter slightly sinks into the chocolate but doesn't hit the bottom, allowing a chocolate base to remain intact beneath the filling. As the peanut butter sits in the base, a second dose of chocolate is deposited on top. This is referred to as the capping phase. The capping head delivers another precise amount of tempered chocolate to completely enrobe the peanut butter core. This top layer seals the filling, ensuring the product is fully enclosed and protected from oxygen, moisture, and contamination. The final thickness of the cap is carefully calibrated, so the chocolate shell is strong enough to hold shape, but still soft enough to bite through easily without excessive crumbling. The assembled cups, now complete with base, filling, and cap, are conveyed into a long, multi-zone cooling tunnel. These tunnels are often 20 to 30 meters in length and feature graduated temperature zones, starting at around 16 degrees Celsius and dropping to 8 to 10 degrees Celsius toward the end. The slow, controlled cooling is essential to prevent condensation or stress fractures in the chocolate. Too rapid a chill can cause bloom or cracking, while uneven cooling can result in misshapen edges or textural inconsistency. Inside the cooling tunnel, conditioned air circulates in laminar flow patterns, ensuring that every cup is exposed to identical cooling conditions. The duration of the tunnel cycle is calibrated to match line speed and product size. Larger Reese's big cups may require longer chill times compared to the classic or miniature versions. At the tunnel exit, the cups are inspected by automated vision systems that detect anomalies like off-center fillings, insufficient chocolate coverage, or edge deformation. Any defective cups are automatically diverted from the line for reprocessing. The cups that pass inspection are ready for packaging. But before that happens, there's one last critical test: weight and sealing verification. Inline check weighers use load cells to weigh each cup or group of cups to ensure they fall within designated tolerances. Simultaneously, barcode scanners and optical sensors check that each product is aligned and properly seated in its paper cup. The final stage before wrapping is an air dusting system that removes chocolate crumbs, static particles, or paper fragments from the surface to ensure a clean, polished presentation in the final package. Packaging of Reese's cups is a high-speed operation. Cups are grouped automatically into configurations appropriate for each product format: singles, twin packs, snack-size multi-packs, or seasonal variations. Each group is loaded into a continuous film wrapping machine, which pulls branded plastic film from a roll, wraps it around the cups, seals it with a heated crimper, and cuts it into individual packages. The film is pre-printed with product information, UPC codes, and freshness dates that were applied earlier by industrial flexographic printers. Once wrapped, the products pass through another metal detector or X-ray system to detect any foreign contamination that may have occurred during packaging, a standard in modern food manufacturing. Any anomaly results in immediate ejection and shutdown of the machine until the issue is resolved. The acceptable product continues to cartoning lines, where it is packed into retail-ready boxes, display trays, or bulk shipping cases depending on the destination. Finished product cartons are coded, palletized by robotic stackers, and shrink-wrapped for transport. Each pallet is labeled with a unique tracking number that links it to its production batch, shift number, ingredient lot codes, and quality control logs. This traceability allows for quick response in case of any issues in the supply chain. Every Reese's Peanut Butter Cup batch is subject to a comprehensive quality assurance protocol from start to finish. While visual inspection, weight checking, and foreign material detection handle surface-level defects, deeper analytical testing is performed regularly throughout production. Factory labs adjacent to the production floor run hourly tests on product samples pulled from the line. These tests measure water activity, pH levels in the peanut filling, chocolate temper index, fat content, and emulsifier concentration. Advanced equipment like near-infrared spectrometers and gas chromatographs are used to validate these metrics with precision. In addition to instrument-based testing, trained sensory panels perform blind evaluations of finished product samples. These panels, often composed of factory employees specially trained in flavor and texture recognition, assess everything from peanut aroma intensity to shell firmness, sugar balance, and mouthfeel contrast between chocolate and filling. Feedback from these panels is compared to golden standard benchmarks. Reference Reese's cups produced under ideal conditions that are stored in temperature and humidity-controlled archives. These control cups are regularly reviewed to ensure no drift in product quality over time. Allergen control is one of the most sophisticated systems running silently beneath the surface of Reese's production. Since peanuts and dairy are both major allergens, Hershey facilities that manufacture Reese's operate under strict protocols to prevent cross-contamination. separate ingredient receiving docks, isolated storage silos, color-coded tool systems, and dedicated air handling zones are used to segregate peanut-related materials from other production lines within the same facility. Sanitation crews follow clean-in-place procedures using food-safe alkaline and acid-based cleaners to remove all traces of allergens between product changeovers. Swab testing for peanut protein residue is conducted on all contact surfaces before production resumes. Hershey also enforces supplier controls. All incoming peanut shipments are tested for aflatoxins, a class of toxic compounds produced by certain molds that can occur in improperly stored peanuts. Only peanuts that pass stringent safety thresholds are accepted, and each delivery is logged and tracked using batch codes that link to the final product's traceability system. This digital record keeping allows Hershey to track every ingredient back to its source farm and forward through every unit sold. But Reese's isn't just a singular product anymore. Over the years, the brand has expanded into dozens of variations: white chocolate cups, dark chocolate, big cups, miniatures, stuffed versions with pretzels, potato chips, Reese's Pieces, or caramel. Each variant requires its own unique processing conditions and introduces new complexity to the factory system. Let's take the white chocolate Reese's as an example. This variation uses a cocoa butter-based confectionery coating rather than traditional milk chocolate. It must be handled in separate melters and tempering systems due to its sensitivity to high heat and faster tendency to bloom. White chocolate also requires precise control of ambient light and humidity during production and packaging, as it is more susceptible to visual imperfections. On the line, switching from standard milk chocolate to white chocolate triggers a full line cleaning and recalibration of depositor and cooler settings. Flavor variants with inclusions, like Reese's with Reese's Pieces inside, add another layer of complexity. In these formats, the peanut butter filling is first blended with the inclusion, pieces, chips, or even candy bits, using slow-speed paddle mixers to avoid crushing or melting the added components. These inclusions alter the viscosity and extrusion behavior of the filling, requiring depositor nozzles to be widened and dosing pumps to be recalibrated for accurate weight control. Additionally, because candy-coated pieces can crack or leak color when exposed to oil migration from the peanut butter, the storage conditions of these fillings must be tightly managed to preserve structural integrity during molding. Even packaging formats are adapted. Big cups, which contain more filling and sometimes additional elements, require thicker paper cups and slightly wider flow wrapping machines to handle the larger size. Seasonal versions, like pumpkin-shaped Reese's for Halloween or tree-shaped cups for Christmas, require completely new mold tooling, reshaped paper cups, and different wrapping film dimensions. These seasonal SKUs are often produced in limited time production runs scheduled between mainline batches, with precise coordination between departments to minimize downtime and clean out inefficiencies. To manage this growing complexity, Hershey's manufacturing ecosystem is deeply integrated with real-time data and automation. Programmable logic controllers govern every stage of production, from peanut grinding to chocolate capping. These controllers constantly adjust conveyor speeds, depositor volumes, oven temperatures, and cooling rates to match product specifications in real time. Sensors along the line feed back information on humidity, belt tension, machine vibration, and material flow. If any parameter drifts beyond the preset tolerance window, an alert is triggered immediately and logged by the manufacturing execution system. The MES serves as the brain of the operation. It logs every batch, shift, operator, ingredient lot, and test result. It manages production schedules based on demand forecasting from Hershey's enterprise planning systems, and it ensures the right packaging, ingredients, and machines are prepared for the next product variation before the current one is even complete. The MES also interfaces with digital traceability systems, allowing Hershey to execute complete recalls if necessary, though this is extremely rare due to the redundant safety nets in place. To support sustainability goals, the factory also measures key environmental metrics. Energy usage from roasting, tempering, and cooling operations is tracked and optimized. Waste heat from roasters is sometimes redirected to preheat water for sanitation systems. Chocolate scrap from edge trimmings and overflows is collected and reworked in designated reclaim tanks. Even the cardboard used for cartons and paper used for wrapping is sourced from certified sustainable forestry programs. Water used in cooling tunnels is recirculated through industrial-grade filtration systems and UV sterilization loops, allowing for multiple reuse cycles before any disposal. Factory roofs are often equipped with solar panels, contributing to the site's renewable energy footprint. These sustainability measures not only support Hershey's corporate goals, they also help reduce operating costs and ensure compliance with international environmental standards, especially for exports to markets with strict eco-regulations. Finally, at the distribution level, finished pallets of Reese's are scanned, shrink-wrapped, and entered into a dynamic warehousing system. Pallet storage is optimized by weight, sell-by date, and destination zone. Reese's products are shipped in refrigerated trucks when needed, although standard varieties are stable at room temperature due to their low water activity and solid fat matrix. Shipments are tracked via GPS and load sensors to ensure they remain within safe handling conditions throughout transit. So when you open a Reese's peanut butter cup and experience the snap of chocolate, the softness of the peanut filling, and the perfectly even texture from edge to edge, what you're actually tasting is the output of a meticulously engineered, continuously monitored, and relentlessly optimized factory system. Behind every wrapper is a chain of roasting drums, tempering tanks, vibration tables, chilled tunnels, microlab samplers, PLCs, conveyors, AI sensors, and hundreds of trained hands working in quiet unison to make every bite familiar, reliable, and timeless. As Reese's peanut butter cups leave the controlled environment of production and are loaded onto outbound trucks, the story doesn't end with the last machine seal or pallet scan. In fact, one of the most underappreciated aspects of the manufacturing system lies in how Reese's maintains product integrity far beyond the factory walls. The journey from factory to store shelf, and ultimately to the consumer's hand, is an extension of the manufacturing process itself. For a product like Reese's, where texture, flavor, and structure are so carefully engineered, maintaining those qualities through shipping, storage, and retail presentation is non-negotiable. Temperature control plays a key role in this extended quality assurance chain. While Reese's peanut butter cups are classified as shelf-stable and do not require refrigeration, they are extremely sensitive to heat and humidity. Elevated temperatures can cause the chocolate to melt or bloom, a condition where cocoa butter rises to the surface and creates a whitish grey coating. Though harmless, bloom gives the appearance of staleness or spoilage and is unacceptable in any retail-facing product. To prevent this, shipping containers and trucks are monitored using digital temperature loggers and GPS trackers. These devices not only ensure compliance with storage requirements, but also provide real-time alerts if conditions fall outside predefined thresholds. Warehousing and retail logistics are optimized with similar care. Distribution centers receiving Reese's shipments are instructed to rotate inventory on a strict first-in, first-out system to preserve freshness. Shelving time is tracked down to the day, with expiration dates digitally logged and printed clearly on all packaging. Retailers are often supplied with merchandising guidelines from Hershey's sales and operations teams, advising on optimal product placement to avoid heat sources and maintain visibility in high traffic zones. This ensures not just product survival, but also consumer engagement. Meanwhile, Hershey's central data systems stay connected to the broader supply chain. Sales velocities from thousands of retail points are monitored using automated inventory systems that integrate with distribution algorithms. If Reese's products are selling faster than expected in one region, perhaps due to a seasonal promotion or viral social media trend, production forecasts and shipment routes are adjusted in near real time to prevent outages. Conversely, if stock is underperforming, the system can slow production or reroute product to a region with higher demand. But what truly sets Reese's apart in this final segment of its manufacturing cycle is its flexibility for innovation and customization, especially on a global scale. Reese's peanut butter cups aren't manufactured identically across every country. Although the core elements remain the same, formulations may be slightly adjusted to meet regional preferences, regulatory standards, or ingredient availability. For example, Reese's produced for the European market may contain non-GMO ingredients or use different emulsifiers to comply with EU food safety regulations. Sugar content, fat ratios, and even packaging inks are tailored to local markets, and each international facility must pass regional audits to ensure compliance with both Hershey's standards and those of the target nation. Seasonal and limited edition Reese's lines introduce another layer of production complexity that extends into post-factory strategy. Every year, variations such as pumpkin-shaped Reese's in October, tree-shaped ones in December, and heart-shaped versions for Valentine's Day hit the shelves. These products require not only physical retooling, custom molds, unique wrappers, modified flow wrappers, but also adjusted production timelines to accommodate pre-holiday distribution. Most holiday variants are produced months in advance to ensure they hit retail shelves in time for the season, but remain fresh through the actual holiday window. To ensure holiday versions meet the same performance standards as core SKUs, Hershey uses accelerated shelf life testing. In these tests, products are stored at elevated temperatures and humidity for a condensed time frame to simulate long-term storage. The samples are then analyzed for fat migration, filling breakdown, wrapper integrity, and flavor degradation. Only those variants that meet Reese's strict internal benchmarks for shelf life, texture stability, and visual appearance are approved for full-scale seasonal release.